Any questions to this? Oh, we got the recording. Question over there.
Yeah, I had a question with the previous slide, actually.
With the previous slide.
So yeah, good example that you mentioned that in and const int is the same.
Yes.
What about auto const? Will const auto will work as well?
Yes, it's the same. So whether you have auto const or const auto, it's the same.
Okay. Thanks.
Is there another question? Please go ahead.
I've got another question from the slide on 148. So for the first example, is now the memory address protected completely, or just when we try to write to that pointer?
I'm not sure I understand the question. Is the memory address protected?
So it's pretty much the same as with the private keyword. It is meant to help you with writing consistent code. That piece of memory can still be written to. The reason that it was pointed also out that the generated code usually can't take advantage of the constness is because the compiler knows that, well, yeah, you declared something as const. Somebody might very well actually modify it through a pointer of some kind. It's really only when a variable has a lifetime that the compiler completely sees and controls, and it sees that, oh, actually nobody is overriding this constness, because, well, you'll see about how you can override the constness, then it might do some optimizations. But again, this is there to help you with writing a code that you can nicely argue about, that you can argue that, hey, this function claims that it's not going to change something. So yeah, but evil code can still do evil stuff.
So we could still do something like assign the memory address to another variable and
absolutely
access it for that.
Absolutely.
Say a equal 5. Huh? Yeah, that's what I was going to say. That if you do a equal to 5 on the line 5, that will be completely fine. You just cannot use it
right.
As a line 4.
Right. So so when you have a pointer to a constant integer, you cannot write through the pointer. But if you have the original variable, you can of course write to that variable directly. Yes. The constant pointer just says that you're not allowed to write through the pointer. So if you give like this pointer to a const into a function, then you know this function is not going to modify my int outside, but outside where I still have the original int, I could write to that. Yes. And also because we talked about the compiler handling const. So const is not just magically going to the operating system and like telling it, look, this memory is protected, please segfault when you write to that. So this is also not what const implies here. Yeah.
I also had one question.
Okay.
So I just wanted to ask about the difference between a pointer and a reference. It seems like they're both accessing memory, a memory slot.
Yes,
right?
Both are there to refer to something.
Okay.
Yeah.
But what makes them, I guess, distinct from each other?
So there are a couple of differences, but there are also historical differences. So pointers were what originally existed in the C programming language, and there were no references in C. Pointers are allowed to be null. So you can declare a pointer and just say it doesn't point anywhere. Pointers can also be rebound. So you can like make a pointer point to an object, and then I assign the pointer to a different address. So they can change where they point to. Whereas anti-head, they need different syntax because I explicitly need to get the address of something to assign it to a pointer. And when I want to read through the pointer, I need to dereference. References, on the other hand, need to be bound immediately when they are created. They can never be made to point anywhere else. And you don't need to take the address to where the reference should point. And you also don't need to dereference them when you want to access what's behind the reference. So references have a nicer syntax and they have more guarantees. But therefore, they can be used in less places. So if you build, for example, a dynamic data structure that has pointers to like other parts of it, like you build a tree-like data structure or a list that always has pointers to the next chunk, and you want to rearrange those, for example, then you could not do this with references because you actually need to be able to make the pointers point to different things during the lifetime of your program.
Okay, thank you.
You're welcome. Okay. Const also can apply to classes, especially on functions, on member functions. And we can put it to the right. And I think this also occurred in a couple exercises already, that we can put a const after the argument, after the parameter list of a member function and before the body starts. And this says that inside this function, the this itself, that one doesn't change. And because the this doesn't change, also all the data members that are inside the class, they don't change. So if I have a class or a struct here and it has a data member and I want to change the data member inside of my member function, then the compiler doesn't allow me. It tells me that the member function is marked as const, as we have here. So we are not allowed to change the state of the class. And this has, and the way the compiler will select this const is if I later have an instance of example. So I create an example, call it E, and I make this example instance const, and then I call foo on that const variable. Then the compiler will pick this foo with the const, because the variable itself was const when I called into its member function. Maybe we should add a line here to have an example of this. Constants is part of the type. So a type T and a type T const are different types in the type system, but the compiler can always add const when it's necessary somewhere. So if I have two functions, one takes an integer reference and the other one takes a reference to a const integer. And now I also have two integers, one is const and the other one isn't. I can call the func that modifies or takes a reference so it can modify internally. It will happily take the A, which it can modify. But if I pass the B, the compiler would error here. It would tell me, look, the function expects a reference that it can modify through, but you're passing it a constant integer that cannot be modified. So this is an error in the type system. And on the other hand, if I call a function that expects a reference to constant integer, then I can pass both of them, because B is already const, and to A, the compiler can just add the const and say, I know I have an integer I can change, but this function doesn't want to change it, so it's fine. I can still create a const reference to this integer that can change. And there will be an exercise on constness in the afternoons. Good. Any questions to const?
By the way, don't worry. Struggling with constness in large code bases is a daily struggle. So expect that you'll be tweaking this in your own code as well.
I have a question about the last slide.
So question online, please.
Why the function constant is does not give a compile error when why?
Why calling the func const on 9 or 10 doesn't give a compile error? Because the func const expects a reference to a constant integer. And for B, this should be clear because B is already a constant integer. And for A, the compiler is allowed to add const to the type. So if you have a type that can change, the compiler is allowed to add the const to the type and then pass a const reference to the func const.
So
because the compiler is allowed to add const, but the compiler is never allowed to remove const.
But at the same time,
so it's a one-way statement. It's a one-way.
Yes, compiler can add const one way. Yeah.
But even besides thinking about it like this, that compiler can add const, just logically, that function says that, hey, I just need a constant object. I don't want to modify it. I just need its state. I just need to read from it. Whether you give it an object that can be modified or an object that cannot be modified, the function's requirement will be fulfilled.
Right.
And I was wondering, although this might be an advanced subject, but this is still sort of the basic behavior of the language, whether we want to mention how these references work with temporary objects.
I don't want to mention this here.
Okay. Fair.
Yes. because then we talk about lifetime extension and temporaries, and that's difficult.
On the previous slide, I
Yes.
believe. Yes. So here, when you declare a function as constant, a member function or method, is that the word?
So in C++, we only have member functions.
Okay.
But in like the conceptual object-oriented designs, they're only methods. So one is theory, one is practice.
I see.
But both the terms apply. So
Right.
Go ahead.
That was not the question anyway. So does this mean that you force this function to treat all of the member variables as constant?
Right. So inside this function, all of these member variables, you can add like an implicit const there.
But then if you have another function, that you can have that function change the variables.
Yes, and you can even overload. So you could add another foo here that is not const, and that could change. And then the compiler would select the right one better based on whether your example instance is const or not.
Right. Interesting. Thanks.
You're welcome. Another question in the back.
Maybe as a final comment, also when functions call each other, constness plays a big role. So a non-const function is allowed to call const functions on the same object, but not the other way around. If you have a foo and a bar function, bar would be marked as a non-const, then inside of foo, you are not allowed to call into bar, but the other way around is allowed.
Gent in orange.
Can you go to next slide? Sorry. So next one. Sorry. So the 150. Yeah. So
50,
line 9. Yeah, I'm giving a, which is not constant, and then therefore in the function will be constant.
Yes.
What if by whatever XY reason in the line 11 I put a equals 5? Still fine?
Yes,
I don't know why I would want to do that, but it's still fine, right? It's just
right.
to prevent inside the function that I will not change anything for a.
Right, because as you said, inside func_const, because func_const takes a const reference, I cannot change through this reference. But outside, I still have an ordinary integer a that I can just write to as I please. Yes.
Okay. So for the compiler, it will understand that a is a const inside the function, but not elsewhere.
Right.
Okay.
Exactly.
Thanks.
So generally, after calling the first function, so on line 7, func a, you cannot expect anything about the value of a after that function has been called. A might be whatever, because the function told you that I might very well change a. After, let's see, line 9, you have sort of a soft guarantee that a will remain the same. It's not an absolute guarantee, but let me rephrase. It's a fairly strong guarantee that a will be the same after the function call as it was before. It's really a broken function setup if it gets modified. But after line 7, you should expect that a might be whatever.
Yeah. Okay. I'll continue because we now took a bit longer than I expected on the constnet, and we had lots of stuff to cover today. We'll talk about exceptions now. And exceptions are there to handle exceptional events. So your program will not always go nicely the way it is intended to. There can sometimes be errors that occur. Stuff that happens, for example, you're talking to a network resource and suddenly the network connection stops working. You're talking to a file. Maybe that file doesn't exist because somebody deleted it in between. There can always be errors in your program or exceptional states, and exceptions are one way to deal with those kinds. It's important, though, that we stress this, that exceptions are there to handle events that happen rarely. Exceptions are not there to handle something that you expect. Like you read a file, you expect that it will contain numbers, and some numbers are not actually numbers. So this is something that you might expect, and then exceptions might not be the right tools. But we can go into like a long philosophical discussion at some point, but that's not the point of this course now. Exceptions are also there to cleanly jump from the place where the error occurred to a place where you can handle the error. So exceptions also introduce more control flow in your program, and they can jump around in your program, which sometimes makes them a bit harder to understand what's going on. But we'll walk through it. In practice, syntax-wise, the way this works is that when we know that exceptions can occur, we can add a try-catch block to our program. And this means within this block, we expect exceptions to happen, and we can try to catch them if they occur. So here on the bottom, I'll open a try block, and then I have an open brace. So that opens a block of code. So everything in between here is under this try block. And then I can add a catch clause. And the catch clause has an argument, which is the type of the exception that I expect that will occur there. And then if inside of process data, if that throws an exception, so if an exception is coming out here, then I have a chance to catch this and do something with this error. We'll talk about this in more detail on the next slides. But in principle, we have the try-catch blocks in the place where we expect exceptions to happen and where we think we can handle those. And then inside some functions where errors could occur on the right side, we can use the throw statement, the throw keyword here, to raise an error, to throw an exception. And we throw, and then here we have a type that is an exception type. And then we throw here, for example, the stood out of range, and we can construct, because this is a class basically, we can construct the out of range with an error message, for example. And then when we throw there, this exception will come out of the function and will propagate up until it finds a try-catch block that catches it. That's the basic functionality. So let's look at those pieces. When we throw exceptions somewhere where an error occurs, and we already said that, for example, here we have a function process data, it gets a file, maybe that file is not open because it couldn't be open, and this is an error. It should never happen that we can't open the file, but whatever. Like the file system could go offline or whatever. And we can throw an exception, for example, stood invalid argument. And there are a lot of exceptions provided by the standard library already that you should use. You can also define your own exceptions, and I think we'll have that later somewhere. Technically, you can throw any type in C++. You could throw an integer. You can see this in practice every now and then. It's really bad. Don't do it. So please always throw standard exception types. And that's the good practice we want to give here. Only throw standard exception classes or your own exceptions that you maybe derive from the standard exceptions. And also always throw by value. So throw stood invalid argument. Don't throw new stood. So don't allocate an exception on the heap and then throw the pointer, for example. So this sometimes happens to people coming from other languages like Java or C#, where they used to throw new whatever exceptions. Like, don't do that in C++. Always throw by value, like you would return by value, throw by value. Right, and we can have many places inside our function where we can throw. Also note, we don't need to say anywhere on the function signature. So here this says void process data, takes a file reference. We don't say that this throws anything. This is just implicit. Every function that can basically throw, unless we put something that we talk about later. I mentioned standard exceptions. They're defined in a few headers. So there's the base class that is stood exception that is defined in the exception header. And it's the base class of all standard exceptions. It has one function here, that is what. It's a really nice name. So when you catch an exception, you can ask it what, and it will tell you an error message. And then like there are further standard exception like runtime error, logic error, out of range, invalid argument, and whatnot. And they all derive, and if you call what on them, they will give you the error message. Also, those standard exception, they can already carry an error message. So you can, for example, construct a runtime error, you pass a message string there, and then you throw that. And then somebody else can catch it and look at the error message, for example. And there are a couple new ones. For example, stood bad alloc that is usually thrown when you ran out of memory somewhere. Like you cannot grow your vector anymore, or like you tried to allocate a block of memory somewhere and you couldn't do that. Then bad alloc is usually the way to do this, to signal this error. When you catch an exception, that's on the other side now on the client code where you try to handle the error. You specify those catch clauses, and you can specify multiple of those. And the catch clauses, they are matched in order. So when an exception is coming out of process data here, the compiler will first look at the first catch clause. can this still invalid argument reference, can this be bound to the exception that comes out of there? So this means the exception that is coming out, is this either a still invalid argument or is it a type that is derived from there? Because I can always bind a reference to the base class to a derived exception. If the compiler fails to match this catch clause, it will try the next one and so forth. So if it's not an invalid argument, then I can try, is it a still exception? And then if it's not a still exception, yeah, that's really bad. Then that exception maybe, so sorry for that. Then the exception is not caught by the second catch handler either. And if an exception is not caught, it will just go up to the next function and it will go up and it will go up. And at some point it can go outside of main. And then what the C++ runtime does, it will call to terminate, which basically kills your process. So if you raise an exception or an exception is thrown somewhere and it propagates up outside of main, your program will be killed. And that is okay. And this is why quite often people put like a very big try catch around their main function to say like, if anything propagates up here, I at least lock the error and then terminate or exit. Yeah, if no catch clauses are there, the exception propagates out. If it's never caught, to terminate. You can rethrow an exception. So if I call again this process data, it could throw an exception. And I catch this. For example, I catch stood bad alloc because maybe this does a big allocation of memory inside. Sometimes this can fail. I know about this. But it shouldn't, but sometimes it does. Then I just want to catch this exception and I want to write like do the error outstream, or I want to write to a log file, or maybe I want to send an email, hey, this machine is under too much load, whatever. You do something. But then you consider, okay, I did something on this error, but the error needs to propagate further because maybe somebody like outside a function that's even more outside needs to handle this. Or maybe I want to make it propagate up until main, so main can say, look, we need to kill the application now because there is no way how we can continue if we ran out of memory. And the way to rethrow is that we just write the throw keyword, but we don't give it an argument. And that just means whatever exception is currently flying, we just throw it up and let's propagate it. And that is the throw semicolon. You can also catch everything. I mentioned before, not all exception types need to be derived from std exception. Some people could just define their own custom exception that you have never heard about. And you can also catch this one, and there's the catch ... So that can be like the final catch clause that catches everything. So even if somebody throws a float, which you should never do, then it would be caught here. The problem is, though, you don't know anything about the exception type here. So you can just say, okay, any error occurred, I have no clue what it was, but at least I can print a statement or like shut down the application gracefully, maybe. Yeah. Okay. And then there is a thing, because when exception is thrown, I'm technically leaving a function. And if that exception propagates up through the next function, we're actually leaving all those functions. So we're leaving a scope. And we discussed scopes on Monday already. Whenever we leave a scope, the objects in the scopes are destroyed. It's the same thing with classes. They have destructors. So if there are local variables inside of a block and I leave this block, then you actually want those to be destroyed. And this process is called stack unwinding, because there's actually a stack of blocks. So like all the local variables for that function, then if it calls another function, you have all the variables of that function and so forth. And that like forms just a pile of those blocks. And when you throw an exception out and it is handled down here, you actually need to start destroying all these blocks and all these local variables. And this is what happens when you throw somewhere. And here's an example. I have a class C. And here's a function f. It creates a C up here. Then it throws an exception. And there is another C down here. Then there is a function G that basically creates another C object here. It calls F. And then there is main. So we have a try block here. We create another C. We call G. We output something and whatnot. So let's try to understand what's going on here. When the main function starts to run, I'll enter the try block. That does nothing. I construct a C. So this will run the constructor of the C class if C had a constructor. Then I call into G over here. I will construct another C. It's called C3. I call into F, we'll jump here. I construct another C that is called C1, and now I throw the exception. So here, I'm leaving the function F. I'm not completing the function F. So this means the variable C2 is not constructed. And it also doesn't need to be destructed because it was not constructed. The function leaves here. It's kind of similar like we had a return statement here, but exceptions go through a different channel. So the exception will be thrown out of F. And because I leave the scope of F, this C1 will be destroyed. Inside of G, the function F has an exception coming out. There is nothing handling the exception inside of G, so the exception will now also throw out of G, which means we're leaving the function G. So we also destroy the variable C3. So out of this G here, an exception is thrown outside. So execution doesn't just continue after C. So like this C out here is not executed because G doesn't return normally, but an exception is coming out. So this exception will be thrown out of G, but it will finally be caught in this catch handler. So this catch handler then stops all this propagation. And at that point where I caught the exception, C1, C3, and C5, so all those that we have constructed before, here and here, they have been destroyed. Now I have the chance to handle this exception. And maybe I want to change something in the system and then try to call the function again or whatever. So that's up to the application logic. But it's important that when I throw, everything that has been constructed so far will be destroyed again. So it's kind of like you roll back a transaction in like a database thinking maybe. It's important that you design your class in a way that if an exception would be thrown, they would release all the resources nicely. And this is why it's important that when your class allocates memory, it acquires a resource, like it opens a file, it creates a network connection, that in the destructor of your class, these resources are properly freed and given back again. Because in the case an error, an exception happens somewhere in your program, and all your classes are destructed one after each other, you want those classes to give back all the resources and roll back what they did. And this idiom, so like this style of having the destructors reverse what the constructors did, is called RAII, and we talk about this at the end of today. But it's very important with exceptions. Here are a couple more good practices. You could talk about exceptions for hours, and there are lots of different opinions. I put a link to the C++ core guidelines here and some more resources for you to look up. But like the most important points from our perspective are that exceptions should be used for unlikely runtime errors. So something that happens really rarely and that is maybe outside of your control. Bad input files. File is unexpectedly not found. Like, you know, you have a config file, it's always there. If it's not there, then you throw, because what should you do? Database connection breaking down because maybe somebody plugged the Ethernet cable. Rare events. Don't use exceptions for logic errors in your code. So you know that, let's say your function can only be called with those kinds of arguments because the function that calls your function needs to set this up properly. Don't use an exception here. It's a programmer's bug if it's called that way. So rather prefer an assert here and try to check this in your tests for your application. Don't use exceptions to provide an alternative return value. So let's say your function returns ints normally, but you know, in a few cases you need to return a string. So don't throw the string and make it catch outside. Like, now I have a different way to return stuff. This is not what exceptions are for. And there are better ways to do this. So if your function has, for example, an optional return rate, it can give you back an int, but sometimes it doesn't. There's a class for that that's called std optional. If your function has multiple different return types, it can return a string or an int depending on the situation. There's std variant for that. We talk about this later. There's also a thing called errno that comes from C. Please don't use it. And also never throw in destructor, because we have seen before when an exception is thrown and the stack starts unwinding, you want to call destructors. What if you, while you're processing an exception, the destructor throws a new exception into the game? Yeah, it's not good. So what C++ will do is will kill your program. When you throw an exception and while destroying all the stuff, you throw another exception into it, then you suddenly have two exceptions in flight. And your program will be killed then. So this is why you should never throw in destructor. Yeah, let's leave it at that. So there's a lot to talk about, but I think that's good enough for now. Here's a more illustrative example. Exceptions are really powerful when there is like lots of code between the error happening and the error handling, for example. And you can also nest those and handle different errors in different places. So this example here, it iterates for a couple of files. So you have files here. So for each files F in those files, you try to process the file. If the file is bad, let's say like there's an error coming out here, then maybe you want to log this error. You want to write this out on the console and say, look, file 1000 something didn't work, continuing with the next one. So after the catch handler, the program just continues normally. So the loop will start again and will process the next file. And inside process file, you try to open the file, but if the file is for some reason not available, then you throw a bad file exception maybe, and you pass in the status of the file. Okay, that's good. And then you maybe read through this file and you try to insert in some kind of database, but maybe the database could be offline. But this is something that should really not happen. But if it really does, then that throws maybe a bad DB exception, and that throws out of the process file. And you see the bad DB is not handled inside the loop. So that exception would actually be thrown out of the loop. So also the loop stops. You throw it out, and then out here you catch the bad DB, and you maybe say, sorry, there was a problem processing your 1000 files. I need to stop here because the database is offline. So you see, you can nest those try-catch blocks. You can decide where you want to handle your errors and also where you want to throw your errors. Here we throw inside the process file if the file is bad, but then inside the database connection, you could have a different error that emerges from further down somewhere in the program. Okay, exceptions are not for free. They carry a certain cost. If an exception is not thrown, so for just opening the try block, having the catch handler, this costs you almost nothing. In most cases, it is actually nothing. But if an exception is actually thrown, there's a very involved process because you need to unwind the stack. You need to call all the destructors. Sometimes it's actually hard for your program to figure out when there's a throw statement, where's the next catch handler that I need to call? So there's actually additional information in your program that tells the program where to jump to, where is the catch handler. So this has some cost to it. So don't use exception like in a very hot loop that needs to crunch a lot of data, and exceptions can happen often here. Then this is not the right tool for the job. So for example, the example I talked before is like, you iterate for a bunch of strings, you want to convert those numbers into integers. And you know, every now and then, like a user just passes, there's an additional character, or maybe this is data you read from a web service, and every now and then there is not an integer there. So you kind of expect that sometimes you cannot convert this to a number. Then the exceptions are a wrong tool, because whenever there's not a number, you invoke the entire exception handling mechanism, and that slows down your program in that place maybe. And then it's better to use something else like std optional. You try to convert the string, sometimes it's not an integer. So then the optional is not set. And you can check the optional here. If it has a value, then you process this. Otherwise, okay, that string wasn't an integer, continue. And that is often better than using an exception, if this is something that happens more often. But as I said, often this is a judgment call. Often there's some philosophy involved. And when you're in doubt, measure. So when you're not sure whether exceptions are causing too much slowdown in your program, you can try to profile the program, see where the hot code is, what takes the runtime of your program. Yeah, I think that's about it. I'll have 1 or 2 minutes more on the no except, and then we can have a discussion again. I can say in C++, because before, if a function doesn't say anything about exceptions, it can throw anything. But because it can throw stuff, and so sometimes the compiler needs to take a bit extra care, because theoretically something could come out of that function. And I can tell the compiler, look, this function f will never throw anything, don't worry about it. And that's what the no except specifier does. I can put that here and tell the compiler no exception will ever come out of this. This doesn't mean f cannot use exceptions internally. So f could throw an exception, but it always needs to handle it internally. The no except just says there will never be an exception coming out of the function. So if an exception would actually occur inside of f and would start to come out, the compiler kills the program because you've broken the promise that you made. A function that is no except allows the compiler to optimize every now and then. It's not like you will get huge gains, but sometimes it can make a difference. There's also a version where you can have no except and then an expression here. So you can like add a condition here. In some cases, it's no except, in some cases it isn't. For example, you can ask whether the size of the long is actually 8 bytes. In that case, the function is no except. But maybe on some kind of different architecture and your program logic really depends on the size of the long, then, and if long is 4 bytes, then you cannot guarantee that this function cannot throw. So that's very niche, but in theory, or like in practice, you can put a condition here as well. The good practice that we want to give you is you can use no except on a function that doesn't call further functions down the line, because otherwise you would really understand what all the functions that get called transitively do. So if your function is no except calls another no except function, that is fine. If your function is no except, you call it another function that is not no except. Exception could come out of here. It could come out of your function maybe, and then the program terminates. So be careful where you put no except or not. Maybe just don't put it. And maybe only put it if you can see in your profiler, it's really causing a problem that this function could potentially throw. So I would rather say it's a tool for experts. And by default, destructors in C++, even if you don't write it, they are no except. So if you throw out of a destructor, your program will be killed because it's implicitly no except the destructor of every class. So that's something to be aware of. If an exception can be thrown inside of your destructor, be aware that you need to catch it and handle it there. If it gets out of the destructor, your program will be killed. Okay, questions? Because I assume there are some. Here, please.
Yeah, I doesn't get it clear probably how the destructors are called when you throw an exception from a class. Is it automatically called?
Yes.
Or always?
Always.
And
yes.
if there is a function when I have several news, for example, some allocations on the heap, what happens then?
Right. So let's say this C5, you didn't put it into a local variable, but you actually have here C pointer C5 is equals new C. So you put the C on the heap, but the local variable here is just the pointer, that's what the compiler sees. So when an exception is thrown out of G and the compiler starts killing all the variables that have been created here before, the compiler sees you have a C pointer here. To destroy a pointer just means throwing away the 8 bytes that the pointer occupied. The compiler will not call delete on a dynamically allocated variable, because you could have passed that point to somebody else. The compiler couldn't ensure that maybe somebody else is using that memory already somewhere. So that's a guarantee that you need to give, that you need to wrap this allocation like in an object that when it's destroyed will also free that additional heap memory. So we talked about smart pointers here and there already. We'll have more in the later on during the course. If you want your dynamically allocated memory to be protected, you need to wrap it into a class that in its destructor will free that memory. That is very important for exception handling to work successfully. Otherwise, you can get memory leaks or resource leaks. For example, you open a file and you just store the file descriptor, just the int there. And then an exception is thrown somewhere and you never reach to the close file, for example. Then you'll have an open file handle that leaks in your program. So you always need to wrap resources into classes that in the destructors will actually clean up those resources. Again, we talk about this later. Questions? So either everybody is afraid now, or it was so clear.
But
yeah.
the
Question online?
but the catchphrase is to me seems it behaves like an if-else statement.
Yeah.
But
so where do we have multiple? it's kind of like if else, but a bit smarter, because you first try, can I match the exception that is in flight against this catch clause? So if the thrown exception is invalid argument or derived from that, then I bind it to this E and I'll use this catch handler. But if it's not an invalid argument or a derived class, I'll try the next one. So it's a similar logic, like if something is that, if it's not, then else if, and whoever, like whatever of the if branches will trigger will finally handle the stuff. So it's a similar way of working here. Yeah.
So it's more similar to the switch case, but it only check an error to handle it later.
Yeah. So the switch statement is also similar, but exception cannot just look at the exception and then jump into one of the alternatives. The compiler actually needs to like check one after the other. But in principle, yes, you take an object and then you try to figure the right branch that can handle that. Yeah. Further questions?
Just wanted to have a comment that you said very rightly that this is a contentious discussion point on exactly how to best use exceptions. What I like to say is, and I think most people agree on this, is that you should never think about exceptions as a method of control flow. That if you try to figure out your program execution, never try to use exceptions to control where your code should go next. That, well, if I manage to open the file, then go here. If I didn't manage to go there, don't use exceptions for such cases. What I like to tell people is that generally, once you draw out the sword of an exception, be prepared for the application to be killed. These exceptions should usually happen pretty close to the application dying. It should not be just, oh, well, okay, something minor happened. But again, there are different schools of thought.
Yeah. I want to add a comment on another school here. It's the school of Google, for example. They say never handle any exception, because if an exception is raised, let it propagate to main and the program should die. If there is an exception, kill the program. But they also then, because they write many like online and web services, if the program dies, like there's a script outside, if the program dies, just restart it. You know, like this actually works for them, for example, but it might not work for your hardware device. It might not work for the cryogenics controls of the LHC. You might have different requirements there.
No, but
it might be different for your analysis that you write. If an exception writes, oh, okay, I log an error, I'll see it, I restart the program. So it also depends a lot on like in what kind of context you're using this program.
But we're not going to talk in this beginner's course about error code, STD error code. Right?
No.
So just to mention that the simplest way, if you have a function which is likely to fail, it has a high chance of failing, just return a variable from it which says whether the function succeeded or it failed. If the failure is an acceptable thing for the function, then it should just return a simple variable, tell its caller that, hey, I failed. And that's a pretty good design for functions where it's sort of expected that it can fail. Optional is one thing, but yeah.
So we talked about optional, where you say like the function usually returns an int, but sometimes it fails to do so, but it's not a big deal. So that is one alternative, but there are many alternatives in many different schools, and we don't have time to talk about all of those. But there are great talks on YouTube, for example. Yeah.
Just because many frameworks do like return codes, and you'll see that in many places that functions that can fail would return a very specific return type.
Yeah. Okay. I heard that coffee is arriving in the back. So I suggest we do templates. That's around 8 slides or so. And then we do the coffee break. So let's look about templates. And templates is a huge topic, but it's also a topic that is often more difficult, because suddenly we talk about not just the way how one function works, but how one function works that can apply to all kinds of types. Because we enter this paradigm of generic programming, of defining functions that can actually have many different shapes. And templates. I got irritated by a concept here. And concepts actually are a language feature that play into templates, but that's also for the advanced course. It's a C++ way to write reusable code. And why it's reusable? Because I can define an algorithm and I can then use this algorithm with various data types. And I can use it with data types that I don't even know yet. Or I can define classes and structs that are parameterized for various types. And templates can be used, as I mentioned, for functions, for classes and structs, but also for variables. And syntax-wise, they look like this. So before I have an ordinary function or a struct or a variable, I have this kind of like one-line introduction that says template. And that means whatever comes afterwards, it has parameters that I can at compile time inject to change the behavior of this thing. And I can have various kinds of parameters. We'll talk about that in a minute, but one of them are, for example, type parameters. So here I define a function that can run on any type T. So, and this T here is a kind of wild card. It's a degree of freedom that I can say this function for any kind of T, it would look like this. And this here is just max. It returns the bigger one of 2 arguments, but it gets a const T reference here on the left, and it gets another const T ref on the right, and it will return a const T reference. Notice I never said this needs to be an int. So I could use this function for ints, I could use it for floats, for doubles, whatever. As long as like this T is allowed to be compared with less than, it will work. If it wouldn't work, I will get an error, but not already here. So just when I define this max function, the compiler will just read through that and it would say, whatever, I'll check later when you provide the actual type for that. Right, and we have the same for struct. So this here is a vector for any kind of type T. You see here this T is used to declare a pointer as a data member. And here I have a variable, which is just a variable called size. But depending on what kind of type parameter I provide, it has a different initializer. So there's the initial value for this variable depends on what kind of parameter I pass in. So let's look about this in some detail. Templates, as I mentioned before, you write them once, but you can create multiple versions of that. And this creation of a version is called template instantiation, because you provide a type, and that the template, there will be like an actual function, an actual struct, an actual variable that will be created from this template. And here I have this example. There is a func. It has one type parameter that is T, and it gets this T as an argument and returns that. So this is like an abstract recipe for the compiler to create versions of that func. And so if I now call func with 3, which is an integer, and the compiler is actually smart, I don't always need to tell it what kind of type parameters it has, because it can figure out in many places. So if I call func3, the compiler will figure out, okay, this argument, it needs to be an integer, because this is the type of the argument here. So this needs to be a func where T is integer. So the compiler will take this function, it will replace all the T's there with int, and it will create this function here. It will instantiate func for T equals int, and that is the version it will produce. If I later call func with 5.2, the compiler will see, okay, here T needs to be a double, so it will create this version of the function. So you see, even though I wrote this function once in my program, if I call it with multiple types, the compiler will actually generate many versions. And that can sometimes lead to a few troubles, because if you instantiate your function with lots of types, you get lots of copies of your functions in your program. So your program can get bigger in size, for example. But it also means that because the compiler, when it calls this function, it needs to actually copy the entire function, produce a version for that specific type. The compiler needs to see the entirety of this function. And this means that this entire function definition must be available to the compiler everywhere it can be called. And we discussed on Monday, for example, when we talked about interfaces and header files and source files, that if I want to have the implementation of a function in one file, but I want to call it from another file, then it's okay if I just provide the signature, the header, so just the first line of the function. If I just provide this in the header file, and then I can call it from another CPP file. This does not work for templates anymore. Because for templates, when the compiler calls a template, it actually needs to read the entire body, make a copy of that, replace all the types, and then put it where it calls. So this usually means that we need to move templates up into header files. And that can also make your compilation slower and whatnot. So there are a couple of drawbacks, but templates are very, very powerful. There are some ways to work around this thing in header files called extern template. I don't want to talk about it. It's rather expertise. Okay, template parameters. There can be various kinds of parameters. And those parameters can be types. You can also have value parameters, and you can also have other templates as parameters to templates. Those are called template parameters. I'm not sure whether we talk about those in the next slides, but it's probably in the advanced course. You can have several of those, and you can also provide default values. So they kind of work similar like function parameters, but now they are like up in like this template head. Here's an example. I have a struct that I call map. So it should represent like key value pairs. So I can like add keys and values to it, and I can get the value for a key. But I want this map to work for any kinds of key types and for any kinds of value types. So I say I have this map. It has 2 degrees of freedoms. You can parameterize what kind of key type it uses, what kind of value type it uses. But if you don't specify anything, then by default, the value type is the same as the key type. So see here, the type parameter key type, it can be used here to provide a default for the value type. And if you don't even provide a key type, then that should just be an integer. And then as you see here down below, I can then use this key type and value types just as placeholders for the actual types that a user would provide later. That's again how templates work. But if I want then to instantiate this type, so I want to create a concrete type with concrete type names inside, then I can pass the template arguments here within angle brackets. So I can say here, I want to have a map opening angle bracket that uses a key type of std_string, and then it uses a value type of integer. Then I close the angle brackets, and now I instantiated a template, and that produces a type now. And this type here, map of std_string int, that is the type of my variable m1. Does that make sense so far? Right. I can also create a map of a float. So in that case, I say I want to have a map where the key type is a float. And because I don't provide a second argument for the value type, that value type will be the same as the key type, which is a float, because I specify float here. So that will create a map of float. And then m2 is a variable of that type map float. And if I don't specify any arguments, then well, the key type by default is int, and the value type is the same as key, so it's also int. So that will create a map of int. And m3 is an instance of that class of that type. Notice if I don't pass any arguments, I still need those open close angle brackets, because the compiler needs to know that this is a template that I want to instantiate here. I see Sebastian turning around. There's a question. Please go ahead.
Yeah, I just, if you don't specify at the first line some default values, would the line 9 be valid?
No. So if I don't provide a default argument for this key type parameter, and I would try to instantiate map with nothing, the compiler would say, look, I found the template map. It has one required parameter. You didn't give me any. The program errors. I cannot compile this. It's the same as a function. It's the same as a function that has an argument where you don't provide a default and you just call it without arguments. The compiler will say, look, there is a function like that, but you need to provide at least one argument. Yeah. Question over there.
I really don't understand the syntax here, because you say that template is, when I write template, everything below is a template.
Yes. So the next entity below. So the struct, so this template here, that introduces this template clause where I can specify all the degrees of freedom that the next thing is going to have. And the next thing is a struct. And here the struct definition ends. So here is also where this templated entity ends. So everything below that one struct now is again non-templated code. Yeah. So the template up here, it only belongs to the next entity. So if we go back here, for example, this template type name, it just goes to the function afterwards. And then when the function definition is complete, also the template is doesn't no longer apply. So if I want to create a new template again, this here is a template struct vector, I need to have a new template clause that applies then to this vector entity. And once that struct definition is complete, then I would need another one because now I want to do a template variable. So each entity that you want to make a template, it needs their own template head.
Okay, clear. Thanks.
Question?
Yeah, this is just a quick one. Just want to double check my understanding. Like line 7, 8, and 9, you're just initializing the template, but you're not actually calling, or you're not actually declaring anything, are you? Or are you?
You're constructing it.
So I specify the arguments for the type. So the compiler will build a type,
Yeah, so you're
maps
saying,
the string int.
yeah, so you're saying key type would be a
std string.
Yeah, and then value type would be an int.
Would be an int. So that alone, until that space, only provides information. So we have a type. Nothing has happened, like no executable code is yet happening. But now I create a variable here.
Yeah, sorry,
so the compiler will at least then do the default construction.
Yeah, no, I understand. So,
yeah.
Maybe we should put curly braces.
We could call braces here, or we could, if that map, for example, had an actual constructor, I could call the constructor here now. Like M1, open brace, constructor argument. So that would work. So that to the left is just, I build a more complex type where the type has actual parameters on how the type is created. Yep.
I really just want to hammer this point about default values. It was said, but I don't know if it sunk in, that with template types, we can refer to already defined template types and use them in the declaration of the next default argument. This is something that you cannot do for function arguments. This is a concept that when you provide default values for function variables, this type of thing you cannot do. But here, this is a very powerful thing that you can do.
Okay.
Hi.
Question.
This is only
Yes,
inside of the one of the templates. You cannot
at
do
line 8,
reuse.
why
Okay, wait.
the
Question
type
online
float
first.
is associated to value type and not and to instead is associated to key type? I don't understand why.
I only got half of the question. The question was whether float here is associated to value type.
Yes, at line 8 we are giving to value type to key type the is given is keep as float, right?
Yeah. So template arguments are matched to the template parameters in the order they are written here. So if I only provide one argument to this template parameter list, then that float will go to the first parameter, which is key type. So key type will be float. But because I don't give a second argument here, the compiler will try to find the default. And that default for value type is that it is the same as key type. And key type is float because we made it float here.
Okay, but in
so
the
that
case...
float here will go to the key type.
Okay. Okay, thank you.
Because value type defaults to be the same as the key type. Oh, if I would not have the equals key type here, then first the template would not compile because I provide a default for key type, but then I have a type parameter that does not have a default. So same as with function default, with function parameter defaults, I need to specify the default starting at the back. So I could not specify default key type, but leave value type open. So I need to provide default starting at the right. Yeah.
So to your question about in which contexts you can refer to types and default types. So as it was mentioned earlier, the template argument really refers to the next thing. In this case, inside of the whole struct, you can refer to both key type and value type however you want. And this includes you defining a templated function inside of the map struct. So you can make templates pretty complicated. If you create a templated function there which has some yet another type, you can make that other type default to, let's say, value type from the encompassing struct. But yeah, these things have to be included in each other.
Yeah. So the type names that are up here, key type, that is really like the name for a type in the entirety of this map. And you can use key type in any place where you could put an ordinary type. Could be a function return type, could be an argument, could also be something else that we haven't talked about yet. Yeah. Okay, I'll continue so we can go to the coffee break. That is just a quick slide because over the years, it changed what kind of keywords you can put up there. Personally, I prefer the type name for type parameters, but you can also put class there. And it has exactly the same meaning. And it's important to point out, even if you say template class T, this T does not need to be a class. You can still instantiate that with an integer. So class here is just the placeholder, can be any type parameter. It just used to be the first keyword that we had in early versions of C++, but it really means the same, whether you put a type name here or whether you put a class here. And again, it doesn't mean that you can only put a class. It can mean any type parameter. Just an important notice. And then there are more things. I mentioned you can have templates as argument to templates. So that's a wicked thing. And there are more places where you can put class instead of type name. They're all equivalent, but some of them might require a new version of C++. So whenever inside the template head you see a class, you can just replace this mentally with type name. It means the same.
But why would a person do that? Why nested templates into templates in the declaration?
Why you would want to do that?
In the declaration.
I think class came first, even before C++ 98 or just around that. Was type name there from the very start?
Type name became a keyword later on during the C++ evolution. I actually don't know it exactly. I assume they had the class keyword first, so they put a class here, and at some point they figured maybe we need something better, or they introduced type name for something else and then figured, yeah, we should actually have it here as well. That's the thing with C++, because it evolved over such a long time, you have certain kinds of baggages that the language carries around.
And since it was used for a couple of years, now we can't ever stop using it.
Yeah.
I think the question was more why you would use template inside template.
Yeah.
And an example. Well,
go ahead.
I don't know.
No, I don't know
example that comes
this
to
is
my
a
mind
fairly
is that you want to
advanced
template
topic,
something with a vector of anything. You need vector because you rely on the fact that you have a vector interface and that you can, resize and so on, but you're happy to work with a vector of anything. So you want to have a template, but the type name that you put inside has to be a vector of anything. So you would write exactly this, and C would be in this case.
This could be std vector, for example. Yeah. You could call func with std vector because std vector had not exactly because it has an allocator, but whatever.
This becomes very complex and it's the advanced course, the expert course.
It's good to know about it, but in order to actually use it in practice, well, come to the advanced course.
Yeah. So this has uses, but not for you now. Okay. When you implement functions that are templates, there are various ways on how you can write those, and we've seen before with classes and therefore with structs. If you have a member function or a method, means the same, you can choose whether you implement this member function directly inside the definition of the class, or whether you just declare how it would look like and then you put the actual definition outside. For templates, it's important to remember that if you put the definition of a member function outside of the class, you need to repeat the template head. This is just something to be aware of. It's just the way C++ works. That if your map has a key type and a value type, then also that member function of map that lives somewhere outside the definition of map, it obviously needs to have the same degrees of freedom. So it belongs to the same template. And if I haven't mentioned this before, this is an out-of-line definition, and up there that's called an inline definition. Both are possible. Some people like that because like in your header files, you usually had your class, you had your one line that describes the function, you move the definitions of the functions in your CPP file. But now with templates, you need to have these definitions up in the header again, but some people still like to have those outside the class. So the class structure is maybe visible and short. And that's when you need to repeat those templates. This is where this comes from. Yeah, you might see this in practice a lot.
And don't be worried, especially at the beginning, if you just prefer putting the function bodies into the classes, just because it's a lot easier to write, especially at first.
Yeah.
And it's worth mentioning here that there is one type of thing which I still to this day do not know how to implement out of line in templates.
How to write this?
But that's an advanced enough topic that no, trust. Well, we can talk afterwards. There is a very a type conversion operator. You tell me how to implement that out of line.
Just stop here. Okay. So let's hurry up the last slide so we can go to coffee break. We have only seen type parameters until now and template parameters. You can also put other kinds of parameters, like all kind of integral types, so int, long, whatever. You can put pointers and also enumerations. Since C++ 17, you can also have auto. That's in the advanced course. And since C++ 20, you can put all types that are so-called literal types, also advanced course, and floating points. So in each iteration of C++, we can put more and more stuff into template parameters. But like basic things for example, just customizing a template on some kind of number. So here I have a polygon. Polygon has a number of sides. And maybe I want to specify at compile time that I want to have a polygon of 19 sides. That is called a non-decagon, by the way. So I can also instantiate a type based on a value. So that works as well. And then I can use this n here inside the definition of this class like it was an ordinary int, or like an ordinary unsigned int. So this n here is just usable as if it was a variable somehow. And again, I can instantiate polygon here with 19. Mind again, because it's a template, if I instantiate a polygon with 18 and then with 17 and then with 16, those are all separate copies because they're different types. They have nothing to do with each other. So polygon 5 and polygon 6 are two different types, two different copies in your program. Comment,
maybe
question?
A comment on why you would do that rather than having it as a member. So there are advantages and disadvantages. The advantages, this is all compile time. And in particular, the line 4 will be pre-computed at compile time mostly. So the 2 times n times sinus pi over n will be done at compile time. And the only thing remaining in your code, in your assembly code, is a single multiplication. Sinus is gone. So that's the interest of templates most of the time. And if you use a 17, 118, 119, okay, you compile 3 times, but you pre-compute the 3 different values.
Right, because everything in this sub-expression here is known at compile time. The compiler can pre-compute this for you. Yep.
And of course, the price to pay is you cannot create, if you have this, you cannot create a polygon of a number of sites that would be runtime given. Like you ask the user how many sites do you want, and you put it. No, that has to be compile time. So you've lost that. So you see the two
design choices that we can make here. Okay, last word on template specialization. So far we have seen instantiation. So this means I have a template with a degree of freedom. I create a version of the template by specifying the arguments. The process of, or maybe not, let's not get into too much detail. I can create versions of the entity that has template arguments and can tell the compiler, look, if your template arguments have certain form or for some specific combination, I want you to produce a different version. of the template. And that is called template specialization. So here we have the polygon that we had on the previous slide, but now I added another template parameter f that describes maybe the floating point type that is used for the computation. That can be float, that can be double, maybe long double, and so forth. And it again has sides. And now I can tell the compiler, look, if you have a polygon that still has an arbitrary f, and so I put another template head here. So I still have 1 degree of freedom for an arbitrary f, but the number of sides is exactly 6. So in that special case where one of the template arguments has the value 6, the other one is still free, then I want you to use that version of the struct and not the one on the top here. And that is called a partial specialization because I provide some of the arguments. I can also do a full specialization and say, okay, if you provide a polygon where the number of sides is 6 and also the data type is int, then you should use this version instead. And the way this works is then when you write down somewhere in your program polygon of, let's say, float 6, the compiler will see, okay, you're going to instantiate the polygon. So it will look up here. Okay, you have two parameters here. They are float and 6. Do I have any specializations that would be a better match for the arguments that you provided? So the compiler will look through all the specialization. If it finds a better one than the default one up here. And if there is a better one, the compiler will use this instead of the generic one. That is template specialization. Okay, you'll have an exercise on that in the afternoon. And that concludes the template chapter. Are there any final questions before we go to coffee break?
Keeping in mind that templates are very good to know about. Again, the more complicated things come to the advanced course.
I think it might go to the specialization. Is there a way to limit the types we allow, like only integer-like types or?
Right. C++20, it's called concepts. Yeah, come to the advanced course.
Earlier, it's
or
type
I fear
traits.
that's the expert course.
Or the extra course that we're planning after the advanced course. No, to answer this question briefly, because you can Google it up. Here I just specified type name f. I didn't specify anything else. So this f can be any type. Instead of type name, I can write something here that says any integral type or any floating point type. And that would tell the compiler this degree of freedom, this f, must satisfy that thing. Yeah. And those are concepts and come back for a later course. Yeah. But the keyword is concepts. And you can Google that if you want.
Yeah, I'm desperately trying to remember the magic keyword, the error in instance or SFINE.
Yeah,
just
if
you want absolutely advanced course, if you want to Google something, because yeah, this has been done since ages, but yeah, that can get really complicated.
Okay, we'll do 20 minutes of coffee break. I guess we'll be back at 10:45. That fine? Sounds good? See you in 20 minutes. Right. Welcome back from break. I can hear the echo in the room. Can people on Zoom hear us?
Yes, we can.
Yes, we can.
That's great. Laser pointers work. Everything all right? Have there been any questions that came up during the break? I'm sure people discussed all about templates over coffee. Any like uncleared stuff? There is actually a question here. If you can have a mic.
Yeah. Me and one of my friends were talking about this use of templates and how you can, I guess, the purpose for a template is to be able to use any kind of type in a function.
Yes.
Right. But couldn't you also just use auto?
Couldn't you just use auto? So auto serves a very similar purpose, and it actually also works with the same template mechanisms and whatnot. I think the biggest difference is the syntax. You can specify auto to let the compiler figure out the types of variables. But if you want to tell the compiler, this is a type that should have parameters, the degrees of freedom, like the syntax that you have in C++ is template type name or so. So it's just a different syntax, but as you said, it makes code generic so it can work with any type. So you achieve the same thing or like a similar thing in both types. In both times, you want to have a generic code, but the syntax is different because grammatically, once you have variables and once you declare actual entities like function structs and globals or variables.
Yeah. Can you these days use auto as a function argument?
You can do as a lambda argument, and then it's a templated lambda. As a function, I'm not sure.
Plus 20. Yeah. So the question was, where is that? Here is a function. You have a function that has a parameter t, and that t is a template. So it can be any type. Since C++ 20, instead of the t, you can also write auto here, and you can omit the template head. So you don't have the template head, but just one of the arguments is auto, and that works in C++ 20. So and there you see the syntax is converging a bit. Yeah.
I was okay with auto return type. That's super useful. Function argument.
Okay, I love it, but philosophy. Anyway, that's probably up for the advanced course. The way this auto works is because it's the most generic version of a concept. So we might discuss this in the advanced or in the expert course that we will give at some point in our lifetime. Okay, let's go to lambdas. Any more questions on templates? Right. Okay, let's talk about lambdas. And before we talk about lambdas, there is a new syntax that I'd like to show to you, and that is called the trailing return type. And since C++ 11, we are allowed to specify the return type in a different place. So in ordinary functions that we have seen so far, when we have a function that is called func, it has arguments and they have names, and then they have the return type on the left. Since C++ 11, I can put an auto in front of the function. So the place where the return type would be, I can put auto. And I can then tell the compiler at the back of the function, that is the type you should return. And I need to write this arrow. So this is a minus and a closing angle bracket. And then I specify the return type. And those are equivalent. They mean the same. But this has a couple of advantages. Because sometimes the return type depends on like the context of the function, or it can depend on a template parameter or stuff like that. So there are various cases where this might be useful. One example here is that if you have a class, and I think we haven't discussed aliases before, but here I just say that my class, it has a type name inside. Oh, we actually discussed aliases, it's like the type def and using. So inside my class, I have a type that's called return type, and it's basically an int. And then I have this function func that returns this return type. If I would now implement this member function outside, I need to repeat the class here because the compiler needs to know that this func is the one from inside the class. But also for the return type, I would need to repeat that because the compiler needs to know it's this return type alias inside of the class. If I use the trailing return type, then I already told the compiler this is the func inside the class. So the compiler already knows we're in the context of this class. So then also those trailing return types, the compiler will look them up inside the body of the class. So this is one way to write this shorter. There are better examples where it matters even more. And since C++ 14, that's also quite important. It's no longer required that you write out this return type. And then the compiler can look into the body of the function and figure out the return type itself. That is useful in some cases. In some other cases, it can lead to confusion because let's say you have a function with 50 lines, it has auto as return type, what it's going to return. Like you need to start reading as somebody who's not familiar with the code. You actually need to start understanding the body of the function to figure out the type. And so does the compiler. When the compiler compiles your program, it also needs to look into the function body to figure out what is the actual return type. So this can also be slower to compile. But there are cases where this is useful. But I'll leave it at this. So there's just this new way that we can define a return type here. And that is used in lambda expressions. So what is a lambda expression? It is a function that has no name. very easily said. It's a function that I can specify somewhere locally where I want to have a thing that behaves like a function, but I don't need to give it a name. I don't define it as a function somewhere outside. And for some reason, we have a Python example here where we use that. So I hope everybody did the Python course before. We have a list of values here that are called data. And now we want to filter this list. And there's a function filter, and we want to filter this data by a function that's that only like either it filters out or it keeps, I actually don't know, the ones that are odd. So I can define a function that I call isOdd, and that just returns whether that argument that is passed is an odd number or not. But you see, it requires us to define this extra function for that. And the purpose of the function is only to be used here. I don't need it anywhere else. So it could be more concise or like more shorter to just put this expression that I want to filter on directly into the place where I call filter. And in Python, I write here lambda and then the expression that should be evaluated here. And we can do the same in C++, and many other languages over the time adopted similar features. So I can have a function that is used locally, and again, it has no name. Here I have a function isOdd that has a name, but here I just define this expression, and the compiler just makes a local unnamed function here that it passes to filter. So in C++, we can do the same, and that's the syntax for it. A lambda expression starts with the open and close brackets, so the square brackets. Then because it's kind of like a function, it has an argument list. Then it has a return type, and that's the trailing return type that we saw already. And then between braces, I have the implementation of the function. I have the body. And then this function here, this lambda function, it returns me an instance of that function. It returns me an object, a thing that I can call. And I can assign this to a variable. And I put auto here on purpose because the compiler will generate a type out of this lambda expression, and I don't know what this type is. So the compiler will just generate a type with no name, and it will give it to me. And this is why in this case, I actually need auto here because I don't know what type this is. The compiler will create one for me. The specification of the return type is optional again, so I can leave this out. And then the return type of the lambda is just figured out by the compiler based on the return statements. And again, f now is an instance of a function object or a functor. We discussed those on Wednesday, I think. So you can think of it like a struct that has a call operator. I think we mentioned this further down the road as well, again. And f is such a type. It's a compiler-generated struct that has this call operator. So it's kind of like a function. But again, I cannot name this type. Example on how I can use this. Here I have an integer array, has a couple of ints. Then I define a lambda function. Starts with the open close brackets. Then it has the argument list. It has one argument, which is an integer. And the implementation within the braces here just prints out this I, bit of text, and then the squared I. And then I can call this f on any integer. So for example, here I write a for loop. It's a range for, so it goes over all the integers in data and then calls f with one after the other. And again, see here, this looks like a function call. So here I have the open close parentheses that call this f, that call the lambda function. Okay, so good so far? Question behind Sebastian.
Sorry, I don't understand. What you say that the lambda function has not name, but f is the name of function.
So
I mean,
yeah, so f is a variable that holds this function for me, but the lambda function itself has no name, and I can also not name the type. And this will become more clear if I don't store the lambda function in a variable, but if let's say like I pass it to a function directly, then I don't even see a variable anywhere that I assign this to. So maybe this becomes clearer later. Yeah. Okay. So so far we have seen lambdas that can have arguments, but lambdas can do more. And lambdas can do what's called a capture. And this is the lambda can also be influenced by the variables that live around the lambda, because I can define the lambda somewhere inside a function. A lambda has access to the other variables that live around it. And something I might want to do is I want to define a lambda function that has, again, an integer argument x, but it wants to add something to this int. So what the lambda function does is it just takes an integer and it returns the integer plus an increment. And this increment is an ordinary variable that lives outside the lambda. But the lambda can see it because it's in the same scope. So the lambda can reach out to this variable here. And then, for example, I can iterate again over this data array here and then call the function I. And then I just make each I equal to whatever the lambda does with that I. So the lambda internally will take each of the integers, add 3, return it, and then I assign this again to the I, which is a reference to each of those elements in the data array. So after this runs, each element in the data array will be incremented by 3. So if I do this, it doesn't work because the compiler tells me, ooh, increment is not captured. So what does that mean? And that's a thing that C++ decided to do, that you cannot automatically have all the state, all the variables around your lambda automatically inside your lambda function, because you could run into troubles with lifetime. Like you could have your lambda, you could return it out from your function, but your lambda actually uses variables that would be gone then, for example. And so C++ wants you to be explicit. What do you want to capture? And those need to be explicitly captured, the variables that you want to use in your lambda function. And this is unlike a couple other languages that don't require you to do this. And the brackets that start the lambda, this is actually called the capture list, and it needs to contain the variables that we want to use in our lambda function. So again, if you have the same example with the increment and our lambda function wants to use the increment inside, we need to tell the compiler, this lambda function is going to use this increment. And then the compiler green lights us. It will tell us, okay, it's fine. You told me you want to have it available. So there you have it. And if you run into troubles because of that, that's on you. And there are a couple ways on how we can capture. And I think we have that now on the next slides. There is, for example, capture by value, which is the default. So again, I have here this function f. And I again have an array of integers. I have an integer sum that lives outside of my lambda function. And now I capture this sum. And then I call f, this f. It will take a couple of integers, and then it will add those integers to the variable sum, which I captured here. And then I iterate over all the integers in my data array. I call the function. So all of these integers are added to sum. Now I'm confused. No, it's actually fine. Okay, the compiler will give me another error and will tell me that the sum that I have here is read-only. Wow, why? Because the sum out here is actually just an ordinary int. It's not const. You could write to it. So why doesn't the compiler allow me to write to the sum internally here? And the reason for this is that by default, variables are captured by value. So your lambda function will hold a copy of these variables outside. And because a lambda function is basically like, this is a body of a call operator. And for lambda functions, this call operator is const. So you can think of this lambda function like a struct that the compiler generated has a call operator that takes an int x, but it has a const specifier here that we don't see in the definition of the lambda function. So that's something to remember, that the call operator, the function, the call operator of a lambda is const. And this is why we cannot modify this sum. It would also be, it would also be wrong if we could modify it, because the lambda function takes a copy of that sum. So we would only add up to a copy of the sum, but we would not modify the sum outside. So clearly, something is wrong here. So what we actually want to do is that the lambda function uses the sum that lives outside the function. And there is a different syntax for that, and that is called capture by reference. Because now I tell the compiler, look, I want you to use the sum variable to capture the sum, but you should capture it by reference. Notice this does not mean take the address of sum. So this is not the address of that we've seen for pointers. It just means the sum variable that lives outside, capture it by reference. So now the lambda function, instead of having a copy of sum, it has a reference to the sum that lives outside. So now when I iterate over this data array, I should actually add all these integers in the lambda function to my sum variable. So that should work. You can mix and match those. So down here, I have the lambda function that has two captures. It captures sum by reference. So the sum inside that will actually work on the variable outside. But offset here is captured by value. So the lambda function will get a copy of the offset that it uses inside. But it doesn't matter that it's a copy because we are not actually changing that in any way. So it doesn't affect the offset outside. Right. So the syntax for the capture list has a couple more things that we can do, because quite often we just want the lambda to just capture everything that's outside by value. So we can tell the compiler, look, figure out what the lambda body uses, and then everything that's used inside here, make a copy and pull it into the lambda. And that is called capture by value for all the variables that the lambda uses. And I can tell the compiler to do this by putting an equals sign here. So all the variables outside the lambda that the lambda uses will be copied into the lambda. If I just put the ampersand, that means everything that the lambda uses, just pull it in by reference. And then again, I can mix those. Some things are forbidden, like you cannot tell it capture everything by value and capture everything by reference. That doesn't make any sense. But you can tell the compiler capture everything by reference, but this B should be a copy inside the lambda. So please capture the B by copy. And vice versa, you can tell the compiler just capture everything by copy, but for B, let's use that as a reference inside the lambda. Right. And that's it for lambdas. I assume there are a couple questions.
Or you might be just so
Questions
confused that not even questions.
So on slide, one before, I believe, the mixed case.
Yeah, this one.
The simple case still. So the variable sum, you give it by reference there, and then I'm adding values to sum inside the lambda.
Mm-hmm.
And for me, this seems like, okay, you find a way how to give sum for the lambda in order to write, because this is how the lambda works.
Right.
But then in the slide after, you are telling me that if you continue next, that actually you can give everything by value if you want. So why would not just give everything by value there? So my question is like, why will by pass it by reference? Because it seems to me like this is one way I need to use a variable that's outside, while I could just put like everything by value. And
I want to modify.
Right. So it really depends on the use case that you want to have. Like that function f, its purpose is to modify the sum that is outside here. So if you would pull a copy of the sum inside here, even though like it wouldn't work and there's a way around that, you actually want your function, your lambda function, to modify the sum outside. So capturing it by value is not what you want. You want to capture it by reference, so it can change the things outside. In some other cases, and I think that's in the advanced course, you want to create a lambda function and you want actually move the lambda function somewhere else. Like you pass it to a different function, you return it or whatever. And then that lambda function moves to a different scope in your program. And if you would capture by reference, it would capture all the other variables that used to be there. But if the lambda goes away out of that scope, like all the local variables would die, and then your lambda would refer to that variables. So you definitely want to capture by copy here. So when you move the lambda somewhere else, you still have copies of the things that are dead by then.
Right.
Yeah, thanks.
Comment exactly the same example without moving the lambda very far. In the mixed case, the offset that you have here, it's set to 1. So your function f, you suppose that it will apply an offset of 1. Imagine that on line 7.5, I put offset equal 2. Now, what do you expect f to do? And there you have the difference between the values and the references, because here you pass by value, meaning you took a copy at the moment offset was 1, so you still expect f to add 1, even if the outside offset went to 2 in the meantime. But of course, if you would take offset by value, then it's really the outside one. So when on line 7.5 you say offset equal 2, then your lambda changes behavior. So you see the different.
Yeah. There's one question in the front. There used to be one over there. Yeah, please go ahead.
Yeah, I just wanted to ask about the in C++. It seems like you cannot use recursive lambdas. So if there is any reason behind this, and if there is any other way, how can you, if you want to use some function which is local in some block of your code, and you don't want it to make it global because you want to keep it only there and you don't need it anywhere else, is there anything else that you can is there any other way how can you use a recursive function which is localized in some block of your code?
Wait. Recursive and function in a function are different. So which one do you mean?
No, a recursive lambda
recursive
function.
lambda.
That's the question.
Yeah, so you cannot use recursive lambdas.
A lambda cannot call itself?
So
I thought it could.
you can do that. Before C++23, there's a workaround. In C++23, you can do it proper. The way this works is because here, when the lambda definition starts, the compiler sees this entire expression, and that is your lambda function. It doesn't have a name yet. So what would you put in here? What would you call inside the body of a lambda function? If you put inside the lambda function f in parentheses, like you try to call the lambda function inside the function, the compiler will tell you, look, there is no f yet, because you're still defining this lambda function, and the compiler needs to parse this definition before it starts to assign it to a variable. So you cannot call f here. I'm trying to remember the workaround.
I think you can create a function pointer beforehand that you capture by reference.
Because I think you can define a std function of that thing somehow. So there's a workaround. In C++23, you can actually, because a lambda function is a class that has a call operator. So the lambda function has like a this. It doesn't, you cannot write this here, yeah? But it kind of has a thing like that. And in C++23, you can explicitly grab this, and then you can call inside the lambda function this. Very advanced. We'll stop here.
Okay, thank you.
Yeah, and to be fair, I never wanted to do this myself so far.
Now I have a question. Why would you want to not give a name to something you want to call? I mean, my workaround is very simple. Make it a regular function with a name because you want to call it, so name it.
Oh, because maybe you want to capture.
Maybe I can comment on why I'm asking this. And when I needed it, I was basically trying to do some kind of the binary tree, and then when creating the nodes, I needed the function to split these, and I wanted to call it recursively, and I just needed in that function which was splitting the node. So I didn't want it to do it global, but that was the only workaround that I managed to design. So that's what I was asking.
So if you run in the case of recursive lambdas, as Sebastian said, you probably want to make it a separate function. Then that is
in an anonymous namespace. We don't cover it in a namespace dedicated to it, if you prefer. I mean, there's plenty of ways to make it local without having a lambda.
Without exposing it to the user.
Question there.
Yeah, I guess more a basic question. And I don't understand why, because you say that, for example, here offset is passed by value.
Yeah.
And but the lambda makes a copy of that.
Yes.
And so why I cannot modify the copy? I don't.
Right. So we have slides that explain this, and they're in the advanced course. And maybe we made the cut at the wrong position, and I should have the slide now. So
this is the same as calling this is passing like a function argument by value. You can modify either one of these, but these will just be two separate.
No, you can. That's the point. You cannot change offset here because the call operator is const.
That's an error, but it's protecting yourself from mistakes, basically. Because what would it mean to modify a copy that anyway will go out of scope immediately?
Where do we have this? Yeah, it's here.
Right, you've changed the value, but it goes out of scope immediately. It's not the outer one, it's the inner one.
Okay.
So it's kind of protecting yourself from kind of stupid mistakes. You may say there's a kind of there's a place where you would do that, but not in Lambda.
So you can do whatever you want inside the scope, and then but outside nothing. Nothing remains. Okay, thanks.
That's cool. I didn't even ever come across this. Okay.
Okay. Question in front?
Yeah, sorry.
Please take the mic.
This is actually going back to the trailing function return type.
Trailing return types.
Yeah. And I was just I'm not sure if you mentioned it, but is return type here, is that like a keyword or
No,
something?
it's just a placeholder for a type
Placeholder.
name. Yep.
Okay.
Int, float.
Exactly.
Okay. So then in that case, then I don't understand the using return type equals int line, because if you're saying, oh no, sorry. Yeah.
No, that's just a type definition up there. And I think this was shown on Monday, how return type is becoming a type definition of int, then it's just int. So that's a separate concept from what was shown afterwards.
Right, okay.
The whole using return type equal int, that's a separate concept.
Yeah, so line 2 and line 3, they don't belong together in any way. It's just often we have classes where we want to specify an alias for a type because my class has like the value type that is float, also
Right, okay.
something like that.
Yeah.
And then later on, I have a function get value. Well, it returned the value type.
Yeah.
Something like that. So it's just the way that I use the C++ language to design my class.
Okay.
And then I want to reuse like the aliases that I created from my class because it makes sense here. Yeah.
Yeah, sure, that makes sense. And just to clarify, this is how you do it before C++ 14. Is that?
You can have both.
You can use lambda in C++ 11.
Yes, lambdas are available in C++ 11, and since C++ 14, you can on ordinary regular functions, because lambda started this idea with the trailing return type. In C++ 11, you can do the trailing return type of functions as well. But in lambdas in 11, I could leave out the return type, and the compiler would figure it out. And people liked it so much that in C++ 14, we decided everybody can do it now. So functions can do it as well.
Yeah.
Yeah.
Okay.
Right. Okay. Then let's dive into one of the biggest chapters we have, the standard template library. Okay, we have 2 more chapters to go. The one on STL is quite big, and then we finish off with RAI and smart pointers. And if we have a couple minutes left, we can still talk about the debugger that we couldn't get done on Wednesday. But we'll see how it goes because the STL is quite large. Okay. What is the standard template library? And the standard template library is a library of standard template. But the most important thing about it is that it comes with your compiler. So when you install a C++ compiler, everybody who uses a C++ compiler and is like roughly on the same C++ standard will have a standard library that offers the same types, the same functions, the same algorithms. They might be implemented slightly different, but they should offer like the same guarantees. They should offer the same functionalities and whatnot. So it's like an agreed upon library that every C++ compiler, vendor, and programmer agreed upon. This is how those standard types should look like. And you have it available the moment you have a C++ compiler. That's why it's so important. It's like the agreed upon types that everybody has. And a standard template library has lots of features. There are strings inside, there are containers, iterators. We have many common algorithms and common functions that everybody needs, common utilities. There are functions to sort stuff. There are functions to allocate memory. We already mentioned function objects, functors. There are various of those there. And the STL is portable. So if you use the string type on, let's say, Windows, it will work the same way on Mac OS, and it should work the same way on Linux and on your embedded system and whatnot, because the C++ standard actually specifies how all of these types must behave. So you can write a program for like on Linux, and it will have a certain behavior, and it should have exactly the same behavior on any other platform. That's what the standard library should guarantee. The standard library is reusable. So it means because lots of stuff is templates, and that's what's so great about it. You can adapt lots of stuff in the standard template library because there are so many templates in there that allow you to specify individual behavior. There are many common algorithms that you can reuse even on types that the standard library doesn't know about yet. So standard library has sorting algorithms, for example, and you can make your types be sorted by the standard library, because you can prepare your types in a way that the standard library can use them and sort them, for example. And usually the standard library is quite efficient. So it doesn't hold true for everything because various reasons. But before you think about whether you should implement a type yourself or you implement your own sorting algorithm, please take the one from the standard library. Only if you can prove that the standard library is slow and you can do it better, then implement your own stuff. But usually pick the things from the standard library. Here's an example. And the first thing you notice is that we need to start including lots of header files because the standard library is divided up into many pieces that are available in different header files. And I don't bore you with all the details. What's up on the horizon is that in C++23, all that goes away. You can just write import std and you have everything available. But that's like a couple of years down the road. What do you have? You have containers. We have seen std vector a couple of times. Std vector is a dynamically allocated array. It can grow, it can shrink, you can add elements to it, can loop over, you can initialize the vector with a couple values. So this vector holds 5, 3, and 4. Then I can create another vector and see it has a different constructor here. So this tells the vector, I want to have a vector of 3 elements. I don't tell it what the values are, and by default, the vector will just create zeros. So that's a vector of 3 zeros. Then I have algorithms like std transform. Std transform takes 1 or 2 input ranges, processes them, and then writes them out to an output range. And the way this works is that I call std transform on in. So in is the vector here, on in begin and in end. So begin and end tell, ask the vector to give it what is called an iterator. We'll talk about iterators later. An iterator to the beginning and the end of the vector. And 2 iterators, begin and end, they describe what is called a range of values. And then std transform can act on this range of values. And then I can describe a second range. So I take in begin again. And because std transform already knows how long this range is based on begin and end, it can take a second range and count as many elements there as well. So I have 2 input ranges here. Here I can specify an iterator to a different thing that will be used as the output, for example. And then I can specify to std transform what it should actually do with the 2 ranges. And in this case, I specify a standard function object that is called multiplies that just takes 2 elements, multiplies it, returns the product. So what std transform will do is it will go over this range 1 and range 2, which in this case are the same vector, pull 2 elements, one left, one right, multiply it, and write the result to the output range. And then move all those iterator forwards. Take the next vectors left and right, compute the product, write it to the next output position. And you see there are lots of moving parts and pieces that you can combine and customize. And we talk about all of those individually now. And the very last line before I answer the question over there, there are many algorithms. And one of them is just plain std copy. But because we can customize so many parts, we can copy, for example, the output vector from begin to its end. So this will copy all the elements in the output vector to an iterator that then acts on a stream. And every time we write to this iterator, it actually writes out on a stream. So there are various adapters on how we can change things to be an iterator again. So we can use it in algorithms. So the STL is very composable and has many pieces that we can put together. And in the end, this will just output like the numbers 5, 3, 4, they are twice, so all of them will be squared, written to the output iterator, and then we copy those numbers to std out, so they're written to the console. Question?
Line 10 should be out instead of in, right?
No. Line 10 here just says I'm taking the same iterator again, so I have in begin as the start of the first range,
okay,
and then I have in begin as the start of the second range. So std transform will iterate over 2 ranges and always take 1, 1, compute something with std multiplies, write it to out. Take the next 2, multiply, write it to out. So that is a transformation that takes 2 input ranges and writes 1 output range.
And take 2 input ranges.
There's also a version with only 1 input and 1 output range. Yeah.
Just to make things simpler.
Okay. I'll continue because many of those things will become clearer when we look at them in detail. So let's maybe defer the questions to a bit later. The STL is huge. So there are lots of stuff here, and I just picked a couple of examples here. And one of the first subpart that we look at are containers. Containers are data structures that we can use to store ranges of elements. And the standard library containers, they don't care about what kind of data type this is, what allocation scheme to use to get memory for those. This can be customized using allocators, and what kind of algorithms you'll be later use on these data structures. That's also independent. And the thing that connects the two, data structures and algorithms, are iterators. Because iterators describe how you can move over your containers, and algorithms work only on iterators. They don't need to know about how the data structures work. And that makes all these pieces nicely decoupled from each other. A couple examples that you might want to use is string to represent sequences of characters. There's also string view, which we don't talk about. There's list, forward list, vector, dec, which is short for double-ended queue, and there's array. All of those are containers that hold a series of values, but they use different ways how to place them in memory. So they have different kind of performances, different guarantees on what happens when you insert in the middle, when you remove from the front, from the end, and so forth. But it should have a common interface. Then there are associative containers, maps, multi-maps, sets. There are flat map, flat set. There are all the unordered maps and sets that use hashing, for example, and give different guarantees. There are container adapters. You can have a stack that you can push and pop to, and that can be wrapped over a list or wrapped over a vector. So those adapt an existing container to make them work like a stack, for example. You see lots of pieces that we can combine with each other. Then there is span that we talk, I think, in the advanced course, and there are a couple more like bit sets, paired as tuple, optional and variant we have seen already today. We also talk about them in the advanced course. And then there's any and expected. So just a short outline of all the things. So when you're ever in the situation and you think, I need to store a tuple of values, I need to have a bit set or something, go up on Google or DuckDuckGo or whatever search engine you like try to find whether there's already something in the standard library that can do what you need. Because very often there are already things that you can use. Oh, that was backward. So I want to pick one example because I think it's one of the most important data structures, that is std vector. And I just want to show you a bit about how std vector works. You can include the vector header, so that gives you the type std vector. And then you can create a vector of some element t. So I put t here on purpose to emphasize std vector works with almost any type. So you can have vector strings of ints of my class, vector of almost anything. I can create a vector and with the elements 3, 5, 3, 4. So in that case, for example, t might be an integer. It's important to note vector has those different constructors, ones with the braces where I specify the elements that I want in a vector. And then I have a constructor with the parentheses that works a bit different. And why this works different, I think we discuss in the advanced course, if we discuss it. So that down here will not create a vector that contains 100, but it will create a vector that has 100 elements that are just default constructed. And for an integer, that would make them 0. So that is a vector of 100 ints. And here that is a vector of 100 ints that are all 42. That's a very frequent source of confusion, like those constructors. So when you create a vector, think, do I want to have a vector of those elements, or do I want to have a vector of a number of elements? And then choose the appropriate braces or parentheses. Vectors can be copied. So when I create a second vector, I copy the other one. This completely duplicates the entire memory. All the elements inside will be copied. You will have 2 independent vectors that each contain all the elements. But you can also move a vector, and we discussed move in the advanced course. This means take the vector over here, move it into this variable. The previous vector is gone, is empty now. And you can actually ask for the number of elements in the vector, whether the vector is empty. Since vectors behave like arrays, you can subscript those. So you can ask, give me the second element of the vector v, and then you can write to that. Or you can access the 1000th element, and that subscript operator returns a reference to the element. Huh? In that case, if you subscript the vector, the vector v, which has 3 elements or 100 elements here, and I access the 1000th element, I'm actually accessing the vector outside of the number of elements it has. This is an error. But in this case, the compiler will not diagnose this. It can maybe if it sees that you literally wrote 1000, but if you access the vector outside of its size, it is very often a runtime error. Your program can crash or can have any other type of behavior. If you call the vector.add function, and you specify what element you want to access, the vector internally does a check, and if your index is out of range, it will throw an exception. So those are the two different ways. You can subscript it. You need to make sure yourself that you're within the range, or you can call .add, and then the program will actually check whether the index is valid. Then you can access the first and the last element. They're called front and back. And since a vector is a dynamically allocated array, you can also ask it to give you a pointer to its storage that it uses underneath. So with v.data, you get a pointer to the elements that are inside the vector.
Maybe on the v.data, that's dangerous, huh? Because the vector may reallocate at some stage in your back.
Right.
And the P is no more pointing to the right thing. That can happen any moment somebody, for example, pushes to the vector.
Yes. We have this here. If you have a vector, you can also ask it for iterators to the beginning and the end. And iterators, they're kind of like pointers. So you kind of get like a pointer to the beginning, a pointer to the end. And it's the same way with the data pointer that Sebastian just said. You get pointers into the internal storage of the vector. But when you then start resizing the vector, so you ask the vector, please resize to be bigger. The vector maybe needs to allocate a new piece of memory underneath and throw the old piece of memory away because it was too small. And suddenly all the pointers and iterators, they would still point to the old piece of memory, and it would just point into nothing. And that can introduce bugs. So if you pull out the guts of a vector, you get the iterators, you get a pointer to some of the elements or so. Make sure that you don't modify the size of the vector while you hold those pointers and references, because the vector might reallocate if you add or remove elements, and then those references and pointers could no longer be valid.
By the way, it's worth mentioning, although it might just confuse things even more, vector iterators are so much like pointers that I think in most implementations, they are literally pointers.
Yes.
A forward iterator, a vector forward iterator is literally just a bare pointer.
We'll talk about iterators in a minute, but iterators are a generalization of pointers. Each pointer is an iterator, but there can be more elaborate iterator types. Yeah. You can also reserve storage for a vector. This is nice if you know I'm going to insert a lot of elements now in the vector. I tell it, okay, look, reserve, make enough space. I'm going to do a lot of insertions now. Then there's vector pushback to add an element to the back of the vector. There's vector insert, where you tell the vector a position where it should insert. Notice this uses iterators again. I ask the beginning of the vector, then I add 3. So I move the iterator to the 3rd position. And please add a default constructed T at this position. Popback removes an element at the back. Erase removes an element at an iterator that I give it. So here I take the end of the vector -3. So pointer to the end of the vector, 3 positions before. At this position, please remove the element. The vector will automatically, if I remove an element in the middle, just move all the elements back together so they're all tightly stored in memory. So whenever I cut out a piece of the vector rearranges the back elements so they're all nicely lined up. So there's actually a cost if I remove elements like in the middle or at the front of the vector. Like all the other elements need to be moved over to their new positions. And then there's clear, and that throws away all the elements in the vector. Right. Any questions to vector? It is the go-to container. So like if you need to store a couple values, the std vector is most often what you're looking for. Question in the back.
We were talking in the previous slide on accessing elements of the vector.
Yeah.
And we had the line 12 and line 13, and line 13 should check if that element exists. What's the performance?
Yes. The reason why those are separate is because inside the add function, you will have an if. It will check if the index that you passed here is larger than the size, throw exception. That branch might have a certain cost. So if you have like a loop that is very hot and you know you're going to loop from 0 to 1,000,000 and that vector has 1,000,000 elements, maybe you don't want to pay for this branch. On the other hand, CPUs are really smart. If they see a branch that's never taken, it also has almost 0 cost. So I don't know. I don't want to give any guidance. It's that's the difference. I very often use the upper version because I trust myself, but actually there's almost no cost in using @. But maybe Sebastian wants to chime in.
Not on this point, on the particularly, but I mean, what is the sentence? Premature optimization is the root,
Is the root of all evil.
Okay,
Yeah.
whatever. Don't do premature optimization. First, it has to work properly, and for this, the is. And as Bernard said, there's between the compilers, the recent processors, and their way to forecast what will happen in the future for the if statements. It's very seldom that this will make a difference. It can happen, but please fix that whenever you see the difference, when you measure it, and when you don't have enough speed. I mean, also compare the time of the price actually of the time lost in the CPU here and the time of engineers or whatever, which will have to be paid for fixing this. And very, very often you better have the code not so efficiently.
Yep. There was another question, I think, in the front. Do you have a question? Okay, then no need. Okay, fine.
Sorry, there is one on Zoom.
There's one question on Zoom. Please go ahead.
I just, on line 3, and then on the second page, the reserve line. Well, the first time I encountered vectors, I told the nicest thing is that you don't need to know how big they are. But, like we are reserving spaces. So can you maybe explain a bit what happens when you reserve, or you say it's going to be a size and then you go over it? What happens and what breaks? Do begin and end break, or do anything?
So Sebastian wants to answer the question.
Yeah, the point is, okay, vector is done for being resized, so there's no problem, it will work. The problem is again about efficiency, and so maybe it will mutilate what I said before. The thing is, you will pay more because you will have to resize. What the vector the way the vector works by default, if you use just a plain vector without the resize, without the reserve, and without saying initially how many elements you have, is that the vector won't create any space. And then when you push the first element, it will allocate some space to put the first element, but it will only allocate space for one element. And when you push the second one, it will say, it doesn't fit. So I allocate for 2 elements. And I have to copy, of course, the first one over and deallocate the space that I allocated initially. When the third element comes, it comes again. And you may say this implementation is completely stupid. No, it's done for big vectors, meaning it doubles each time. So it will go to 4 and then to 8, 16, and so on. And at some stage, you will allocate quite a bunch in one go. But for small vectors, if you have vectors of 10, 20, even 100, you can imagine that you have 4, 5 reallocations and all the copies going with it in the meantime. And in modern processors, an if statement, as we said before, doesn't cost anything basically because the processor already knows in advance whether it will be yes or no somehow. But memory allocation is extremely costful, or can be extremely costful, depends which allocator you have in the back. Yeah, you can also handle it another way, but can be very costful. So the reserve statement maybe make a difference.
Yeah. So the rule of thumb is when you know that you're going to fill a vector with lots of values, it's very worthwhile to reserve space for those. Even sometimes if you don't know exactly, but I'm going to insert at least 900 elements, so I can reserve to size plus 900. And if it's a couple more, okay, maybe I'll pay for another reallocation.
No, but this is exactly the point, that if you know that there will be a lot, you can even just make an estimate that, well, on average, there will be 500,000 elements in here. So let's always reserve 500,000 if you can afford it, memory-wise, because then maybe you'll have to do 1 reallocation afterwards if your estimate was a bit low, but you won't have to do 10 reallocations.
Yeah. Question.
Thanks.
I have.
By the way, there's somebody at the door outside. Attila, could you maybe open? Thanks. Please go ahead. Question.
Yeah, I have a more general question about the containers. What are the limitations? How many elements they can store?
Right. When you run out of memory in your machine.
So it's just done by the size of the RAM you have.
Pretty much.
And
yes.
the swap space and
there.
Yes.
There are like cases like if you compile for, let's say, like 32-bit architectures where like your size T's are smaller and whatever, you could actually run out of the number of elements that a 32-bit integer could describe. But like nowadays, most people have 64-bit architectures where the integers are all big enough to describe more elements than your RAM could fit. So it's usually the physical RAM that's the limit. And then if your machine can swap out to the hard disk, then you have even more. Yeah. Okay, one more question. And then we continue, because otherwise we can't finish.
So I didn't understand one thing, because if, for example, I don't know how many elements my vector will have,
yeah,
I still can push back, but
you can always push back.
Yeah,
yes,
but
yes. It's not a problem. What we are discussing here, and let's clarify this.
This is an optimization.
This is an optimization. On first order, when you start writing some piece of code where you try to figure out some algorithmic approach to something, you wouldn't even start putting any of this in there. You would just create a vector, you would start pushing back into it. That code will work fine. It is just once you have some nice algorithm that does for you what you want, let's say finding, I don't know, muons of some properties. Once you want to optimize that code, then you should be thinking of these things.
Yeah. Last comment, then
Yes.
we move on.
I just wanted to quickly go back to the question about the index access operator versus the add function. I just hammered this into a benchmark thing, and on a modern CPU, there's absolutely no runtime difference by running through 1 million elements, if linearly. So yeah, there might be a cost, but often there's no cost.
Yeah. Right. Okay, let's continue before I start making comments. We talked about iterators a couple times. Iterators you can think of as a generalization of pointers. So pointers point somewhere in memory. Let me think, did we discuss, I think we discussed pointer arithmetic. This means you can have a pointer to an element, and then you can do +1, and then that pointer will move to the next whatever element it is in memory. So pointers have, iterators have the same behavior. You can have an iterator to some position somewhere. You can do ++, or you can do on some iterators +10, and then the iterators will move forward. But because iterators are more general, they can also work like on linked data structures. You imagine you have a list of items that uses pointers to point always to the next element, and they're crisscross in memory. You could have an iterator that when you tell it to move by 10 positions, it would not literally in the physical addresses move by 10 addresses, but actually look like, where do I need to go for the next element? It's here, and the next, and then over there, and go for 10 positions like this. And that is the generalization of iterators. It's just, I have an iterator that describes some kind of position in my container, in my sequence. And by moving it around, it moves logically in this sequence back and forth. But this order doesn't need to be physically the same as the memory addresses. And this is what's more general with an iterator compared to a pointer. Iterators are used to iterate over some kind of data, and they're independent of what kind of container are used. So even though like vector has its own iterator, list has its iterator, deck has their own iterator, the way what you can do with an iterator is the same. I can do ++ on any iterator, and it will move it to the next, independent if it's the vector iterator or the list iterator. And whether that is like an iterator to integers or floats, doesn't matter. And what kind of algorithm is used on top. So even that doesn't matter. A couple examples that we have are reverse iterators, back insert iterators, because you can make iterators that when you +1 them, they actually move backward, because you say, I want to have now my algorithm that regards the entire sequence as being reversed. So I just wrap a reverse iterator over the normal iterator, and now everything just works mirrored backward, for example. So that's one way to customize. And here I have an example. I have a vector of integers. And then I use the R end. So that's the reverse end. So that's actually the beginning of the vector. And then I have a loop that takes an iterator to the reverse beginning. And as long as this doesn't reach the reverse end, I move the iterator 2 positions forwards, which actually moves it 2 backwards. And that way I can write an algorithm that just like by just messing with the way the positions work, the iterators work, you can have different behaviors. You don't need to fully understand the example. It's just about what kind of capabilities are there. And then there are algorithms. And there are so many. I think we just show a couple examples later on. And those are generic implementations. Algorithms are typically expressed on iterators. So the moment you have iterators to your data structure, you can usually use any of the algorithms in the standard library. And a couple of those examples are for each. You just want to do something for each element. You want to find an element. You want to count how many of those elements satisfy a certain condition. You want to sort the elements. You want to transform that we have seen before. You want to get the minimum or the maximum, or you want to reduce all the elements to a single value, given like a function that always computes the result of combining two elements. And then you run this over a sequence to reduce the sequence of values into one. For example, to compute the sum of all the elements or the product. I put a link to a talk here. It's a cool talk. It shows you 105 STL algorithms in 1 hour. So if you can spare 1 hour of time or so, you can learn about 105 of those algorithms. We mentioned function objects before. They are structs that have a call operator, and they are used in lots of places of the standard library. There are a couple of ready to use, like there's std plus, std minus, and they basically just take 2 arguments, do the plus or the minus, and so forth. Nowadays, you should use lambda functions for that, but they are still there and you can see them in a lot of places. But maybe let's look at a quick example and then show the lambda case. Here I have a vector of values, and now I have a variable that describes that I want to increment by 42, and now I want to transform this vector 1, 2, 3, and just increment all of the values by 42. So I could call std transform, and I transform the range that starts at the begin iterator until the end iterator. And as an output, I use the same iterator again. So I'm basically reading in the range, but I'm writing to the same range out. So also that can work. And then I pass in a function object that is this incrementer. This incrementer holds the increment. It can be constructed by this increment. And in the call operator, it receives a value. And that's one of the values of this range here in the transform. So one of the integers in the vector. It adds the increment and then returns it. So std transform writes out those return values to the output iterator. And that's what std transform does. It will call this incrementer on each of the elements in the vector and write the outputs back into the vector. And I think we have the lambda example here nowadays. It's very often shorter to just write a lambda function. So that made a difference when you used to have all the C++ versions. Nowadays, I think you can express everything with lambda functions, which are usually nicer to read. So here I capture the increment, and then I transform the vector from begin to end, write again out at begin, and then the value. Notice here, previously I had v.begin, and now I call begin on v. It's a different syntax that works here. Just ignore this for now.
Especially because you didn't put std.
Yes, which you don't need here because it's an ADL call, but forget it. Okay, good practice. Use the STL algorithms with lambdas. So whenever you can write a lambda function instead of defining your own functor, so maybe use the lambda, it's usually easier to read. Sometimes you find in code bases stuff like bind second, pointer fun, and even though it contains the word fun, it's actually not fun to work with this type. It's like a function, pointer, adapter, whatever. Just don't do this. And if you see code like this, maybe you can rewrite it with a lambda function, make it nicer. Okay, a couple more things for the STL. We already talked about the range for loop. So before we had the range for loop, we used explicit iterator loops. And you can see now that, for example, the std vector template, it has a nested type that is called iterator. And that's the way how you figure out what is actually the iterator type for my container. So I can ask the vector for that. That's the type of it. And then I call v_begin, so that gives me an iterator to the begin. And then until that iterator is not the end of the vector, I loop. And in each loop iteration, I'll plus the iterator. So I'll move through the positions of the vector until I reach the end of the vector. And then I can read through the iterator by dereferencing it. Notice again, iterators are kind of like pointers. I can plus them, and by dereferencing, I read through the iterator. In C++11, I can use the range for. So this works nicely because std vector has begin and end, and the range for will find begin and end and basically does all this iterator magic for you. So the code down here and up here is the same. And using the STL, you could do the same. Instead of manually writing a loop, you could just use one of the algorithms that does that. And the algorithm in that case is called std accumulate. and you call it from begin to the end of vector, you start with 0, and to that 0, you start accumulating all the elements of the vector, and then it will return the result. And in C++17, you have a different algorithm that offers some different guarantees that is called std_reduce. So you can also tell it reduce this range of elements into 1, and by default, std_reduce will plus them. But you could customize. You could do std_reduce and multiply all the elements together, for example. I think there will be an exercise on that. Here are a couple more examples. So they're just for you to see what kind of pieces you can find in the STL. There's, for example, std_list, which is a different container. Then you have find_if that finds an element, or it finds the first element from begin to end of that list that satisfies this condition. So std_find will go through the elements. If the lambda returns true, this is the thing you will get out. So it's basically find the first element for which this lambda function is true. And so forth. There are a couple more. Like we had the vector, we had transform already. You can see like there's so many pieces that you can customize and put together. It's really very, very versatile. And we had std_reduce already as well. A different example that you might need quite often is I have a vector of values. I want to remove all the duplicates. That's a frequent case. And the way you do is like you sort the vector, then you call std_unique, which does not remove the elements that are duplicates, but it will move all of them to the end of the vector. And it will give you a new iterator to where all the duplicates start. And then you can tell the vector, okay, now erase all the elements from this new end and the actual end of the vector, and then you throw away all the duplicates. That's something you need quite often. And there is also an algorithm called std_removeIf that removes all the elements in the vector that return true for a certain predicate. So here you have a lambda function, and if that function returns true, you throw out the element. But this does the same. It just moves all the elements that should be removed to the back, returns you the iterator where those elements start that should be removed, and then you need to do the removing in a separate step. As again, those are two patterns that you will likely write quite often. That's why they are here. In C++20, there's a shorter way. There's a new algorithm called std_eraseIf, and you can just do this in one step. Okay, welcome to Lego programming. I mentioned it so many times already because the STL is composed of so many pieces that are really well thought out and can be combined in many interesting ways. They're like, I myself discover use cases every now and then again on how I can use those algorithms. They're really, really versatile. So use those. And if it's not immediately obvious how it's done in the STL, for sure there is a way you can figure out to make use of it. So please think twice or thrice before you implement algorithms yourself. There are for sure already some in the STL that can help you. Okay, there's an exercise on the STL in the afternoon where you play with a bunch of vectors and randomize those. Final note again, be brave and persistent. The STL is large, has lots of moving parts, maybe a bit hard to understand, but it's definitely worth your time. And C++20 will add lots of more cool stuff to that. It's extremely powerful and helpful. Okay, questions to the STL? One question over there.
I noticed that pointer function, the not funny thing, and
the PTRFN.
Yeah,
fun.
Bind to second.
Yeah, exactly. Forget about them, please.
Yeah, I think they are deprecated since 17.
Good.
But is there any reason to not use, for example, bind or function or other STL?
Yes, there's std_bind, which you can use in a couple places. So std_bind is one of the better ones because in C++11 we got variadic stuff, so that's more useful. And so you can use that, but in many, many cases, a lambda function is just easier to read and easier to understand. So when you start using std_bind, for example, think, can I express this in a lambda? It's probably nicer and easier to read.
Okay, so you recommend to use lambdas?
I would recommend to use lambdas, yeah.
Thank you.
As somebody who wrote an extended amount of algorithmic code using the old formalism in C++98 back in the day, yes, use lambdas. The whole code became a whole lot simpler and much easier to read.
Yeah. Okay. So we have around 7-8 minutes to go. So it seems like we don't get to the debugger. So Which basically means you're not allowed to make any mistakes over the next half a year, because you'll only learn in summer how to debug. No, just kidding. So like ask your colleagues.
But I imagine the instructors told them a little bit about it on Wednesday.
Some mentors on Wednesday already showed some stuff on the debuggers. Yeah. Okay, then let's embark on the last chapter, which is about RAII and smart pointers. And was there a question? No. Okay. So why do we need this? And one reason why they exist is because pointers sometimes can be error prone. Pointers are sometimes hard to use, or they have certain drawbacks, and we can very easily create bugs with them. And one example we have here is that we can create a pointer to a character. Maybe we forgot to initialize it, or maybe we actually initialize it down here, but then we have a foo up here. Just because we refactored the code, we introduced a function call here, and that can throw, and we can catch down here. And down here, we actually really rely that this s is initialized. If the foo function here throws, then we know the lines below here, they're not actually run. So our variable s will stay uninitialized, and that is probably a bug. So that is bad. That can segfault. That creates a bug here if foo ever throws an exception. So not good. Pointers need to be released. So when I figured out I need to immediately initialize the variable when I declare, I read into this. Oh yeah, but if the first character is a hash, it's a kind of comment, then I can return out of here. It's fine. Whoops, who deletes that s? Because every memory that I allocate manually with new, I must call delete, but I have my delete here. But yeah, at some point I figured if the line starts with the hash, I return early because then my program is fast, but I forgot to also delete it up here. So that's something I can forget. That's an error I can make and produce a memory leak. And pointers need clear ownership. I have, again here, I create a pointer, manually allocate it, I read into it, I push it into a vector. I also push it into a set. And now I give this vector to one part of the program and the set to a different part of the program. Yeah, whose pointer is it now? Who needs to clean it up? Who needs to delete it? It's not clear here. And that is another, again, a source of bugs. When it's not clear who owns that piece, who is the piece of code that must destroy it. Could somebody please open the door again? Thanks. So who should release that? Not clear. Let's walk up to that. And that problem not only exists for dynamic memory, but for any kind of resource. And one resource could be a file, for example. And in C code, very old code, there was a call, or there's still a call, it's called fopen, and that opens a file, and it returns a file handle, and that is a still file pointer. Notice this is not a pointer that you're supposed to delete with delete operator, but you need to pass it to fclose to close that file again. We can also lose this handle and leak this handle because let's see. We create a vector, we write some stuff and whatever, we put some stuff into this file handle, so we write to this file. For some reason, we return an error, or we encounter an error that we reach the end of the file, maybe disk space runs out, whatever, something. And then I return early here. Or maybe an exception is thrown in some of those cases. And similar as we forgot the delete on the previous slide, I could forgot to close the file here. So it's the same problem. I created a resource, I allocated a piece of memory, but I forgot to give it back. I forgot to free it. So, and one paradigm, one idea on how to address this in C++ is called RAII. And it stands for Resource Acquisition is Initialization. And it's a very stupid acronym because it doesn't tell you at all what it means. But the way it works is that we use a variable that has a constructor and a destructor. And we use the semantics of the scope where this variable is defined. So in the constructor of that variable, we get the resource, we allocate the memory, we open the file. And in the destructor of that variable, we close the file, we release the memory, close the database connection, whatever. So constructor always acquires the resource. So the initialization of the variable is the acquisition of the resource. And the destruction of the variable is the releasing, the freeing of the resource. And we wrap all the resources inside such classes. That is the idea. And then we create instances of these classes on the stack. So we don't say new the file thing, but we just put the file thing on the stack. So when we return from the function, when an exception is thrown, when we leave the scope where this variable is defined, the constructor is really run, the destructor is run to release it. Example, I can create a class file, and now I call studf open that opens the file inside the constructor of my class. And I store this file handle here in mhandle, which is declared down here. And then very important, in the destructor of the file, I close this file handle again. So again, constructor acquires the resource, destructor releases the resource. I can then offer additional functionality to write to this file maybe or whatever. So that is open for design. But the important thing is that the constructor gets it, the destructor gives it free, gives it away. Example here, I have a log function and I use this file class. So again, the constructor here, I pass in the file name, it opens the file. So this log file now holds this file handle. And then I write to that. And then when we run out of the scope, so when the scope ends, the compiler will destroy this file and it will run the destructor, and then the file handle will be closed. And if that write function here, for some reason, it throws an exception, then we also leave the scope here of that function, and the file will also be closed, even in the case of an exception. And that's the nice thing about this. The good practice is please don't write your own file class. There was one in the standard library. It's called studfstream. So use those to handle files. But it's like an illustrative example here. OK. And now we have a similar thing for memory. And there's a standard type for that. And that is called studUniquePointer. And that is a pointer type that follows this RAII pattern. It wraps and behaves like a regular pointer. You can even get the pointer out by calling .get on the unique pointer. And when it is destroyed, it deletes the object the pointer points to. So it calls delete on that piece of memory that the unique pointer holds. Unique pointers have move-only semantics. We'll talk about move semantics in the advanced course. But for you to remember is that if you have a unique pointer to an object, only this one unique pointer is allowed to hold that object. You cannot copy the unique pointer and have two unique pointers hold the same object, because then suddenly it would no longer be clear who owns it now. And the design of unique pointer is such that there can only ever be one unique pointer that holds the thing. So when you want to then move ownership, like from one function to another, so you need to move the unique pointer. And we see this in a bit. So here we have a function that takes a unique pointer to a foo. Notice we need the memory header. And then it behaves like a pointer. So I can write the arrow and then bar, which is a function of foo. So it kind of behaves like a pointer. At the end of f, this unique pointer goes out of scope. So it will delete the foo that it holds inside. If I now create a unique pointer outside, I can pass it a pointer to a thing that I allocated. So I can call new foo here. I allocate memory. I create a resource, but I immediately give it to the unique pointer to hold it. And then if I want to call the function f with the unique pointer, I need to move the unique pointer over to that function. You need to take the studMove as a magic thing for now. We talk about this in the advanced course. But this is our way to tell it, look, this unique pointer should now go from here over to there. And now after the function f is run, the unique pointer is actually empty. So when I call get to get the pointer out, it's null. Because what the unique pointer does, it will give over this resource to somebody else. So the unique pointer that remains is just an empty shell. Okay, what do you expect if I don't call studMove? So I have a function takes the unique pointer, I have a unique pointer outside, and I just pass this unique pointer here. What would happen? Anybody wants to make a guess? Wild guess, come on. Everybody's just dreaming about lunch, I see. Okay, I reveal it. It will be a compiler error. The compiler will tell you, oh, you call a deleted constructor of studUniquePointer, because the way unique pointer is implemented, it is that it has the copy constructor deleted. And because f takes a unique pointer by value, the C++ language would pull a copy here of the unique pointer, but then when it looks up how the copy is implemented, it would see, oh, it's actually forbidden. And then it will error. And that's how the unique pointer works. So the compiler would tell you this is not allowed because that would violate the idea of the unique pointer. Suddenly you would have two. There's a helper function called std_make_unique that allocates and constructs the object. You pass in a couple arguments to the object that you want to construct, and it allocates memory, constructs the object, and creates the unique pointer all in one go. So it's a utility function. Why we mention this is because it was introduced in C++ 14, 3 years after the original unique pointer. So if you have a very old code base, you might not see that yet there. The nice benefit of having std_make_unique is you will never have to write a new or a delete in your code base again. So if you systematically avoid new and delete and always use unique pointers and later maybe shared pointer, you actually can no longer build a memory leak. You can make some weird cases where you have like cyclic unique point, cyclic point, whatever. But like if you are careful with using make unique and smart pointers, you will probably no longer have memory leaks in your program. It's really nice. Example, we have the file class from before. We remember it has a constructor with a string. I can call std_make_unique that file, and then I pass the constructor arguments from my file. And make_unique will take those arguments, allocate memory, pass the arguments to the constructor of a file, and then wrap a unique pointer around that. And this is what comes back. So this f here is a unique pointer of a file. And then I can use this again as it were a normal pointer. And at the end of scope, it would delete that file, which means it would destruct the file and then release the memory. Okay. When to use what? Always use RAII if you hold a resource. If you hold a resource that needs to be deleted at some point, always use a class that uses this RAII pattern. So you never need to release anything yourself again. You never need to deallocate something again. If you have pointers and you need to own that memory, use a unique pointer. We see a second smart pointer in a bit, but always use a smart pointer. Only if you want to point to something else that you don't own, like somewhere there lives an object and you want to pass to a function, like a pointer to the thing so it can read or modify the other thing, but you don't want to hand over ownership. You don't give the responsibility of cleaning up that thing to the function. Then you can use a raw pointer, only when it's about to refer to something, but it's not about ownership. If you want to express that you own this memory and you have the duty to release it, please use an RAII class or use a unique pointer. To summarize this, we have a function here that creates some kind of T. It allocates it on the heap, it returns it, and now it's your duty to manage it. You express this by returning a unique pointer to the T. This function produces a T, and now I'll give it to you, and you're responsible for cleaning it up again. This is what unique pointer expresses here. And if I have a function observe, and I call those down here, by the way, so when I call produce, I get the unique pointer out. I store the unique pointer here. Now I have ownership of the unique pointer. I hold the resource. It's my duty to clean it up. When I want to call a function that just observes this value, it just wants to look at the T that's inside, I pass this by const reference. So observe will just look at the T, it will not modify it, it will just maybe read from it. If I want to modify that thing that the unique pointer stores, I can pass it by reference. So I can dereference the unique pointer, but then pass a reference to the thing to another function. So the other function can change this T, can write to it, but I still don't hand the ownership away. I don't give away the object. I just provide read access to it and write access, but I don't give away the duty to manage it. The same if I pass the pointer to somewhere else, I can ask the unique pointer to give me the raw pointer out. I pass it to somebody else. It still does not give away the ownership. I still retain outside in my function the duty to free that thing. Only if I want to pass this duty on, I can then call a function that then expects the unique pointer to tell me that, look, you're going to give me a T, and I also want to receive all the responsibilities that come with this thing. And then I need to call std_move here to move this unique pointer into the next function. And now I'm released of the duty to release it. And I think that's it on unique pointer. So the unique pointer is about lifetime management. So it's nice that it frees the resource at the end, but like there's this higher level concept. You have a unique pointer when you want to own a thing and you want to govern how long you're responsible for it. You tie the lifetime of the object to this unique pointer instance. So this unique pointer is an RAII type that manages the lifetime of the thing on the heap memory. Use raw pointers or references if you just want to refer to something without messing with the lifetime. Use the std make unique function to create a unique pointer. Try to have no new and delete in your code. In very rare cases, you can avoid it, but try to have as few of them as possible. You just minimize the memory leaks you have. And if you just want to have a dynamic array, std vector may be more useful than having a unique pointer of something. Right. Any questions to unique pointer? I have 5 more slides on shared pointer, and then we're done for today. I don't know if it's 5, but just made that up.
Just a simple
yes, question.
In the example in the previous slide,
yeah,
when you have a function that returns a unique pointer, in principle, a function returns by copy, but a unique pointer do not have copy.
Right. I didn't show you the implementation of the function. It's because if you have a return statement and you return a value here, since C++ 11 and then also like in later version of C++, those values will be implicitly moved because the compiler knows, because it sees a return statement, you're going to end the function here. So the variable that occurs in the return statement can also be moved out. So in short, the compiler makes this work.
It's not even moved anymore in C++ 17.
Yes, because you have copy elision. Yeah. But like conceptually, the compiler will make this work. You can return a unique pointer by value. The compiler will make it work. Yeah. At the back.
I think it's just a typo on line 10. Should be consumer, not consume.
Right.
Yes.
Thank you. Good. Okay, last slide. One more question? Go ahead.
Just I have in my code a lot of new deletes.
Yes.
So the best practice will be just to remove all of them, and instead of each new, put make unique and the same copy just what was in the new th1 something. I just put it there.
Yes. So first, you can even before that ask yourself the question, does this need to even live on the heap? Because very often you can just put your variable as a local variable and it's fine. You can just put it on a stack. Right. If you need to put it on the heap, make sure it's wrapped in a smart pointer. So make sure you put it in a unique pointer and a shared pointer. Yes, you should not have a new or delete there.
But you did touch on a pretty touchy subject of
how
all of the root interfaces are sort of old style things. But try to, even when you create root objects, try to create them inside of unique pointers. There are some subtleties there, but yeah, in general, you can do this. Because, you know, root has its own ownership of objects, but on first order, yes, you can just put everything into.
Okay, so let's finish off with shared pointer before our lunch gets cold. Shared pointer is similar to unique pointer in the sense of that it manages a piece of dynamically allocated memory for you. But in comparison to unique pointer, which has this unique ownership, there can only be one unique pointer that manages. Now a shared pointer can have several owners. So you can allocate an object on the heap and then have arbitrarily many shared pointers that all point to the same object on the heap. So as unique pointer, it wraps a regular pointer. You can move a shared pointer, but you can also make copies of the shared pointer. And it uses internally a technique that's called reference counting. So the shared pointer keeps track how many shared pointers exist that manage this object. And once that count goes down to 0, the last shared pointer to the object is destroyed. Then you will also destroy the object that you refer to. So that's like the last person that goes out of the room should turn the lights off. So the last shared pointer that is destroyed will then also destroy the object. This tracking of how many shared pointers exist, it requires a bit of overhead. It's in principle thread safe. So if you have a shared pointer, you create a copy, you pass one to one thread, one to another thread, and like several threads concurrently copy and destroy shared pointers. This is all fine. Still, the last thread with the last instance that is destructed will clean up that resource. But it has a bit of overhead. Don't worry about it. Measure if it gets a problem. Similar as with unique pointer, there's a std make shared. And then again, the type that you want to create, you can optionally pass arguments that creates an instance of a shared pointer. Internally, the shared pointer will now have a reference count of 1 because there's one shared pointer that manages the foo here, and that is that SP. If I push this into a vector, I take a copy of the shared pointer, give it to the vector. Now I have 2 shared pointers. So internally, they will have a reference count of 2. And then if I insert it into, let's say, a set or so, then now I have 3 shared pointers living that all hold this one foo. Reference count is 3. And now if that scope ends, then this local SP here is destroyed. So the shared pointer count will drop back to 2 because the vector and the set still hold a shared pointer, but the local shared pointer was destroyed. Okay, so here's a little quiz. Yeah, let's run through this quickly. You create this one integer, make shared of one integer, it has the value 100. That is in shared. What is the reference count here? Just shout it out. 1? Yeah, you have 1 shared pointer. Now I define this lambda function here. It captures the shared pointer by value. So after line 2, after I created this lambda function, how many shared pointers are in existence? I see it 2 in the back. Yes, because I still have the shared pointer outside, but now the lambda function that is inside, that is stored in print, it has a copy of the shared pointer. So I have 2 shared pointers. I call print, that doesn't change anything here. Then I open a new scope, I create a copy of the shared pointer again. What's the use count? How many shared pointers exist? 1, 2, 2? Should be 3. Is a shared pointer outside, the shared pointer living in a lambda, and the shared pointer that I created with the copy here. I can access through the shared pointer and increment that integer, that's fine, can print it again. At the end of the scope, what happens? You destroy that shared pointer here, the PTR. So the use count should drop to 2 again. Let's see if we were right. So the first print here, that's use count 2. Inside here we have 3, and then down there we have 2 again. Right. So if I change this shared pointer here and capture it by reference, what would change? The lambda function doesn't have a copy of the shared pointer now, so all the use count should be 1 less. So you see, we stay at 1 use count, and only inside this extra scope where I pull the copy, I have 2 shared pointers. Otherwise, I always has 1 shared pointer that exists. Right. You'll have an exercise on smart pointers in the end. I think you need to find a memory leak or a bug there. And that brings us to the end of the course. Any questions on shared pointers?
I do my usual comment, don't use them unless you really need. And you said already that it was customized.
Right, right.
It's very seldom. Basically, you only use them when you do multi-threading stuff and you're sharing state between threads. That's basically the usage.
So the best practices is if you can put it on the stack as a local variable, do it. If you need to put it on the heap, use a unique pointer. If you actually manage an array, std vector is probably what you want to have. You will need a shared pointer in very rare cases. So it should not be the default. So many years back, many people figured, oh, now we have shared pointers in C++, we use it everywhere. It's not a good thing, because with shared pointer, it's not clear who actually owns the thing, and it's not clear when will the resource actually be deleted. So if you have a file in the shared pointer, you don't know when the file will be destroyed and closed, because even though you maybe release your shared pointer, somebody could still hold it somewhere else, maybe even in a different thread. So it carries this indeterminism that a unique pointer doesn't have. With a unique pointer, you know when the unique pointer is destroyed, that thing dies with it. And that's worth something to know that. One question here.
My naive understanding always was that heavy objects should be created on the heap and the light ones on the stack, right?
Right.
So whatever root thing I'm using is usually quite heavy, right? Like the histograms with a lot of the bins and stuff like this. So I should probably always use the pointers to that?
No. So it's a bit more complicated than this. In general, this is sort of a good guiding principle. But most of the more complicated objects themselves, let's say a root histogram, that will have its own memory management for the array that it uses behind the scenes for the individual bins of your histogram. You should, if you only need a histogram, let's say temporarily, just create it on the stack. That works perfectly fine. In the background, TH1 will have its own memory management for making sure that everything is set up. It will actually allocate some memory on the heap for this. But you are absolutely welcome to just create that object on the stack yourself. Just like with std vector, the std vector can be huge. It can be gigabytes in size, but the vector object itself, it's a size and a pointer. That's a small thing. You can, well, okay, but
it's just
you
small,
can
yeah.
pass it around, pass the std vector around. Well, as long as you move it around, it will always be very safe to move around. So, yeah, unfortunately, it's more of a shades of gray thing with where you should be creating various things. The heap is still very good for a large class of things. We still use heap memory for a lot of things, even high-level objects, but not for everything.
I mean, maybe just to conclude on that, you should, in principle, always use the stack, just because whenever you need the heap, you will use a vector, you will use the histogram of root or whatever, some class that is provided by something else, doing the memory management, doing it with smart pointers or whatever inside, but you don't care that much. That class is doing it for you. And if ever you're doing a new kind of fancy histogram, whatever, at that moment you will have the question and you will deal with the heap and you will have a new or actually a make unique at least somewhere. But normally, if you just reuse a library, you want it's everything on the stack.
Okay, one more comment.
I just merged a little update to the exercise instructions. So you have the smart pointers exercise that Bernard just mentioned, but it's going to go way far. So it's going to go to depth of shared pointer management and so on, which is probably not for now. So what I would tell you, and it's also now in the new set of slides, you work on problem 1 and problem 2. If you feel like it and you want to play with shared pointer a bit, you can work on problem 3, but that's completely optional. If you update your instructions, or if you go to GitHub right now, you will see the new instructions.
Okay, super. Any final questions? No. Then I'll thank everybody for joining in. That concludes all the morning lectures. It was a pleasure to work with you. You'll still have afternoon exercises today. Well, I hope you enjoyed the course. I think there will be a post-training survey that Stefan Reuser will send around, so we can gather some feedback for you, because we always want to improve ourselves on the course. And then, you know, if you really liked it and you want to know more, there's the advanced course in summer that Stefan Reuser already mentioned. Thank you very much, and enjoy your Friday and have a nice weekend.